think I fixed the next 3 hours. I don't know what'll happen in the 4th hour. So I make my slides in VS Code, which probably, as you know, is just a web browser in disguise, right? And so whatever way the VS, I wonder if they work in Chrome. Whatever way the VS Code, like, HTML runtime interprets my column widths is different than how Firefox does it. And that's, like, unsurprising, but, like, very annoying, right? Because, like...
Yeah. Sometimes, what do you call it? The format, the size.
Yeah.
If you copy your code from, like, Firefox to Chrome, then sometimes,
Yeah.
changes.
That's definitely what happened. Yeah, and I'm, like, not a web developer, so whenever that happens, I'm like, guess it won't work. Like, I don't know how to fix it, right? And I'll learn to fix it eventually, but, like, it's annoying, right? Like, but also that's one of the reasons I write the automata are written in code, right? Because I can always just run that code again and get whatever I want. I would like there to be a little more auto-scaling, but I'm using this Quarto thing, which I like well enough. It is for data scientists, and the data scientists definitely don't understand web development. Like, I'm guessing they just all use the same web browser, and I don't know which one it is. But, like, okay. So, man, my throat's, like, hurting again already. I might have to, like, maybe, like, tomorrow afternoon, we'll just have to do more exercises or something so my voice makes it through the 3 days. Here's the deal. We introduced deterministic finite automata before lunch, right? And then right before we went to lunch, we started teasing non-deterministic finite automata. Do you really have to understand non-deterministic finite automata? No, you probably do have to understand deterministic finite automata because that's very close to just understanding control flow. But you don't have to understand it with the words I use. My planned homework on this is I'm going to actually make you write the code that turns an NFA into a DFA, and that turns, it's very hard to go the other direction from a regular language to a DFA, but it's pretty easy to go from a DFA to a regular language. So that's sort of my plan here, and I was going to do that instead of having you write proofs, just write some Python scripts. So building up towards that, the way to show that regular expressions and deterministic finite automata, no, I can't say it that way. The way to show that languages generated by regular expressions can be recognized by deterministic finite automata, and vice versa, is by showing closures for the finite automata under union, concatenation, and star. We showed that we could do union pretty easily, and we showed that doing concatenation without non-determinism is hard. And in fact, I got pretty far through writing the proof using determinism, and what I was doing was basically writing the non-determinism proof. So it makes much more sense to just actually do the non-determinism and then have that whole powerful truth technique than to do it in each one. So I almost think of non-deterministic finite automata as code factorization for proofs. It's frequently would be nice to be able to say these things are non-deterministic. We can prove its equivalent, so we do so. Not every one of these works that way. But what we're going to do is we're going to do union, concatenation, and star, and then we can show the equivalence. So let's make sure we're recording. Okay. So we already did union. And we did it with DFAs. But we had to do, like, you remember that proof, right? We took the two DFAs, we made the pairs of all of their states, and then we had this annoying thing with the accepting state that actually happened to look a lot like an NFA. Let's just use an NFA for that, right? So we're gonna redo that proof, and you're never under any obligation to redo a proof, right? So why are we showing the proof? Well, because we're gonna do other proofs, and it makes sense to cover this. Okay, so we're gonna prove the result This is also going to have the benefit of showing NFAs are closed under union, which we can kind of assume they are, but like we can also write the proof there. So this is the original proof I wrote with all of the sort of, mostly the delta thing being pretty interesting, right? And that is an incomplete specification of that delta, right? That's only the output. So, okay, what are we going to do now? We're going to argue for the same thing, that these things are closed under union. That if I have deterministic or non-deterministic finite automata that recognizes some language and another one that recognizes another language, I can just make a machine that recognizes that combination.
Both of them.
Yeah. So I'm going to take both M1 and M2. And I'm just going to run them both at the same time. I'm not going to like pretend I'm doing one and pretend I'm doing the other one at the same time, right? I'm just going to give them the same start state. And I'm going to say, non-deterministically, by the power of magic, I will follow, on the very first time I pick a state transition, I will go into the correct automata to recognize or reject whatever string I have. And then it'll just stay in that automata and keep going. And this is unbelievably easy. I am going to demonstrate that it can be made rigorous, but it is basically sufficient to argue this. It's like, hey, right before you read the first letter, you pick which one you're going to use, and then you just use that one for the rest of it. It's just almost like the addition of the two of them, right? It has all the states that both of them have, but it's not the pairs of states. It just has every state. Okay? I'm going to show this in a few ways, right? So first thing we're going to do is we're going to make the new Q. Very easy. The new union NFA set of states is not the union of the Q1 and Q2 states, because we probably have a state called Q1 in both of these things, and we need to keep all of those states separately. So we can renumber them if needed. There's a few ways to describe this. I've seen the term disjoint union used in two ways, but there's a mathematical operation wherein you can take two sets that might contain the same elements and you give them indices related to which set they're coming from, and then renumber them. So now instead of having two state Q1s, which we likely have, we have Q1 sub 0 and Q1 sub 1, or something like that. We're also going to add a novel start state, and it's going to have no return edges. This new start state is just to split up the computation before we go into our two NFAs. And these are NFAs. These are not deterministic. Q1 and Q2, which we're using to refer to the start states of M1 and M2, which are the two we're taking unions over. They're still around, but they're no longer the start state. What they have now is they do all the same things they used to do, but instead of having an incoming edge from the start state, they have an incoming edge from our novel start state, Q0. So I take a Q0 and I put it way before both of the machines. Then I have an edge that goes to Q1 and Q2. Yeah. And then otherwise they're identical. So this little box, I don't know how clear it is, but that's firm
Union.
right angles. Disjoint union. This is union.
Oh.
This is, we do the renumbering and make sure we keep the same number of elements. The difference between this one, this is how I think of it, is the cardinality of that is exactly the same as the sum of the cardinalities. Whereas sometimes you take a union of two sets and you gain no new elements, right? So if I take the union of 1, 2, 3, and 1, 2, I have 3 elements. If I take the disjoint union of 1, 2, 3, and 1, 2, then I have 5 elements.
Both like they joined.
Mm-hmm. Yeah, so I don't call them 1, 2, 3, and 1, 2. Now I call them 1 sub 1, 1 sub 2.
One sub
Right. Yeah. And this is actually yes. Here's one way to say it. The members of the union are indexed by the initial state, by whatever their initial set is to avoid multiplication. There is entire mathematical theory behind doing this disjoint union operation. I felt actually very uncomfortable using it at first. I looked into it and convinced myself it's fine. If you don't like this, your homework's to look into it and feel good about it, right? But it wasn't too bad for me to think about it in terms of like, well, if these are mathematical objects in a computer, and I'm storing them in 32-bit data types. Well, now I just store them in 64-bit data types, and I store the name of the object in the top 32 bits, and it's only twice as big, right? And that is still much, much smaller than having all pairs. All right, we're going to make a new delta. What's the new delta going to be? Not too bad. We're going to once again do something very, very close to the addition. An old delta took a state and a letter and returned a new state. No problem. What are those mathematical objects really? Well, that's actually an ordered pair of what is itself an ordered pair, the state and the letter. So you take that, and that's the first element of the pair, and the second element of the pair is the new set. Well, what that means is that these deltas are just sets of ordered pairs. I can just set union them. Or disjoint union them. It doesn't matter, right? Because I've renumbered all of my states, so they're all going to be the same now. There'll be no overlapping. So I just take D1 and D2, and by that, I mean I just take this the union. Disjoint or otherwise, it doesn't matter. They're all equivalent. So what this means, graphically, is perhaps the easier way to think of it is all of the arrows on M1 and all of the arrows on M2, they stay exactly where I left them. No other changes. The novel Q0 does matter a little bit. I do need to add 2 new edges connecting Q0 to the graph, because I can't have multiple start states. So that's the only reason we have to add this phantom new edge Q0, or new state, I guess, right? And it's kind of the abstract idea of a state. So it's just there's a node somewhere, and the edges coming out of it are labeled with the empty string. So it's just you can immediately start in either Q1 or Q2, and we model it with a Q0. Q0 is the new Q0 we created. The accepting state is also a disjoint union. We don't care which M1 or M2 accepts. We don't even care if both of them accept. We would never check. We're just going to non-deterministically pick one of them that does accept if they do. We'll accept from that one. Let's look at this visually, and this is what I just fixed. See how it fits on the screen now?
Yes.
I told it to make this exactly 300 pixels wide, and that's what worked. This is a 1920 by 1080 viewport, and I said that's 300 pixels, so I don't know what math it's doing internally, but that is not 300 pixels. So someday I'll figure out my web development. We should recognize both of these. This was our example of a two-state machine, right? 0, 1, 0. We did the negation of this in Paint. This was for 0 terminated strings, right? This is a 1 terminated string. Yeah. And this contains 2 ones that are adjacent, right? 1, 1 next to each other, and then you're always happy. Let's combine them. So what are we going to do? First thing we're going to do is renumber. What is the only thing I changed? I don't know if you saw that when I pressed next. These are now R's.
Oh, Q1.
Yeah. I was like, I can do triple subscripts, or I can change Q to R.
Renumber.
Yep. I think R is alphabetically maybe after Q too. Yeah, QRS.
QRS.
Yeah, so I just did. And this is common. There's one interesting one later that I think goes like VWXYZ, right? And you like have to skip U because U is used for something else. I don't know. The way letters are chosen is quite funny. We won't talk about it too much this term, even though it would be in this class. But something I like a lot is Alonzo Church's lambda calculus. And it's, what's the lambda stand for? And it was the Greek letter he hadn't used for anything yet in the paper. That's how he chose lambda. So like that's what we do. It's the letter we haven't used yet in the paper. So that's R. Okay, I'm going to put them next to each other. So what's going on here? Separate? Now they're next to each other. Yeah. Nothing too exciting here. But you see, this is not an NFA or a DFA at this time. And why not? Because it has 2 start states. So I'm going to solve that problem. I'm going to solve that problem by adding a Q naught. If this looks kind of sketchy, what's going on here? Well, Q naught is pretending to be what could be the start state for this automaton, right? So if Q naught were behaving as Q1, it would have a 0 edge going to Q1, and it would have a 1 edge going to Q2. So I have both of those. This has the same edges. as this. Outgoing, only outgoing. The incoming edges come into this one. Same thing up here. Q0 also pretends to be R1. R1 has an outgoing edge to itself, labeled 0, and an outgoing edge to R2, labeled 1. Trivial. And then the other way to do it is I get rid of these ones, and then I put the empty string there. And it's logically applicable. And that is also why we can use the empty string, because you can always do something like this. Essentially just two machines running in parallel. Boom. Python multiprocessing library, forks in Bash, key threads in C, different containers in the cloud, right? We always can do multiprocessing, and usually we have some process that kicks off the two multiprocessing, right? So this is our container daemon or host or something that kicks off the two things. This is the equivalent form with the no string edges. So if I say, I can non-deterministically progress from Q0 to R1 without reading anything, or to Q1 without reading anything, same thing. To me, this is actually less clear. I don't prefer this as much, but I cannot argue that it takes less space. There's fewer edges, right? So whatever forms of complexity bother you, to me, it is harder for me to think about things with the null string in them, so I don't. But they're all logically equivalent. I'm reiterating that I can turn this thing into a DFA. Which DFA can I turn it into? That is an exercise for you if you want to know. But do note, 1, 2, 3, 4, 5, 6 states, which means our DFA will have 2 to the 6th states, which is how many? Do you know?
Actually, I don't understand the question. I mean, like, can you repeat the question?
Right, okay. This is an NFA. What makes it non-deterministic? Those are the same, and they come out of the same one, which means this has an intersection, right? So this must be non-deterministic. Since this is non-deterministic, I can make it deterministic, because I've proven I can make things deterministic. The way we make things non-deterministic is the way we make a non-deterministic thing be deterministic is we simulate non-determinism. And the way we simulate non-determinism is we store a set of possible states rather than use all of the actual states. All of the possible states for this thing are 1, 2, 3, 4, 5, 6. 6 states. Now, that means the non-deterministic one has 6 states. The deterministic one would have to have a state for each element of the power set, which is 2 to the 6th. Because for each one of these states, it can be either part of or not part of.
Not part.
So I can represent it as a bit string with length 6. So I could number all of these things 0 through 2 to the 6th. Or it would be 1 through 2 to the 6th. Right? And 2 to the 6th is 64.
64.
Right. So this is a relatively complicated NFA, right? I can represent it with strictly fewer than 64 states in a DFA. One of the reasons that you know that this can be modeled with many fewer states is that and you never want to think about this too much because it's easy to make mistakes and it's hard. There's only one point of non-determinism, which means that at any given time, you only have to look at the combinations of these states. So you actually have this state or this state, and this state or this state or this state. That's only 6 combinations. Because you can't be in this state and this state at the same time. So this is actually quite easy to model deterministically, though it is more painful to lay out. And that's why we just used it as a proof technique. It doesn't really cost us anything. It doesn't cause any problems. It's just easier to write as proof. And so, what do we have here? I think I duplicated these L's by accident. I think that's a typographical error. Yes. For all NFAs, there exists a DFA such that the language of the NFA is equivalent to the language of the DFA. This was our proof. If you recall, we were able to preserve the same delta, but we had to use power sets, and that our accept state was quite complicated. Close Discord. It's starting to get warm. I don't know what chip is in here that's causing heat, because I expected the heat to come from the power, but the power is plugged in on this side. Okay. Here's theorem 1, now restructured to be an NFA proof. You notice we no longer make any claims that these are specifically DFAs. We simply claim they are machines. They could be DFAs or NFAs. We don't care. There's a language of each machine. For M1 and M2, they each have a corresponding language. We take the union of the languages. So that M1 is a function from bit strings to true false. So this is the set of bit strings which return true. This is the union of those sets. We can create, this is a set of bit strings. M1 returns true on that set. That's what it means. That's how we go back and forth between languages and machines, right? This is how we specify the machines. We have Q1 and Q2. Those are our sets of states. Disjoint union, and we add a start state. We use the same letters. Of course we do. We take the disjoint union of the deltas, and then what do we additionally add? We incorporate our new start state. And all it does is connect to the existing start states. Nothing else, and it requires nothing to transmit. We specify that this is now our start state, and now you see why we use Q0. And then we take the disjoint accept states. Oops. Now we can concatenate, and that's good because we really wanted to concatenate. The number of times where you see a theorem or a proof just assume you can do concatenation with strings is very stressful to me. Every once in a while you'll see a notation where someone concatenates machines, just acting like the machine is the same as its language. It's fine if your audience understands that, but it's very confusing to me because I don't imagine when you put 2 6 tuples next to each other that corresponds to combining 2 languages, right? So we're going to be a little careful with concatenation. Concatenation, you'll remember, was the problem where we couldn't figure out when we were starting to read a string if it contained. We wanted to have even number of zeros, then odd number of zeros, or vice versa. Makes no difference, right? And so somehow we have to know when we start reading the string if we're going to have an even or odd number of zeros. And we solved that problem by not caring. And the way we don't care is using non-determinism. So we are going to create M3 such that the language of M3 is the concatenation of M1 and M2. How are we going to do that? Well, we're going to create a new DFA, or NFA. And that NFA is going to have some states in it. What states? Well, the same states we already have, right? This one is quite easy. As with union, so with concatenation, we're going to take the disjoint union of these 2 states. Why is that? Well, essentially, looking ahead, we're going to imagine, well, we're going to need to model all of the same things, just one after the other, so we can reuse all the same states. Delta's not too bad either. We need the same arrows between all of our states. We're just going to need some additional arrows connecting things. You remember the naive approach, where we said, it'd be really nice if we could just have arrows going from the accept states of M1 to the start state of M2. And we can have that now because we have non-determinism. The reason we couldn't have it before was we didn't have non-determinism. So we're going to take the disjoint union of the 2 deltas, no problem. And then we're going to add something. How are we going to get from M1 to M2? We're going to add empty string paths or edges or labels to note, whatever, however you want to think of the arrows connecting things. And for each element of the accepting states of M1, we will create one directed edge labeled with the empty string to the starting state of M2. So, the new Turing machine, the new finite automata has the delta of the old finite automata, the delta of the other old finite automata, then for every element of the accepting states of the first finite automata has an edge going into the starting state of the new finite, the second finite automata. We use the same initial state as M1, because we're going to read that first in our concatenation. And then we're going to use the same accepting states as M2, because we're not going to accept until we've completed the concatenation. I know what you're thinking. You're thinking, what if the second automata accepts the empty string? That's not what you're thinking. That's okay. If you're worried about that, we just mark either the start state of the second finite automata as an accepting state, which is a little bit sketchy, so you have to be careful with that, or we do a directed edge straight to the accepting state. Were you thinking something other than that? Do you have a question? Okay, you got this?
I was just processing it.
Yeah.
But
Yeah, this one's not too bad because it's sequential, right? This is writing a function that calls another function at the end. Just not that bad, right? And how you can think of this, right, is, well, actually calling a function is very similar to doing two concatenations, where you take the calling function, you split it into two things, you deconcatenate it, right? And then you put a called function in the middle. So to me, union is these branches, like if statements and for statements. This, to me, is calling functions.
How does it deconcatenate?
You just imagine it conceptually however you would, right? So if I'm writing a program, right, and somewhere in it I call a function, well, one way I can think of that is, well, I can actually take another deterministic finite automata that corresponds to the called function and just plug it in there. And what does plug it in mean? Well, it means concatenate. So concatenate is sort of the maximally powerful form, where we take just the combination of two languages. But you can also use it just for part of a computation, right? And if we think of perhaps a modern program or even a piece of software as maybe being a combination of scripts, right? It is a concatenation of scripts, right? And so then concatenation is how we stitch together small pieces of code into larger things. And for me, rather than thinking of scripts, I always think of functions. Function is the atomic unit. That's maybe the smallest amount of computation I think of, or that's the abstraction I think that splits things. So you can always concatenate together functions in any way, and we just proved it. Right? This means, essentially, this is the reason why you can call functions in programming languages. Maybe it's more helpful to think of code blocks, right? So I've been doing a lot of this work this semester in Python, but in the C programming language, and I think in JavaScript as well, there's this notion of a code block, which doesn't have to be a function or not a function or the body of a loop or something. You can always just put curly brackets and then write a code block. And they have special rules, so like variables are only defined inside the code block, right? And so usually this is how we create local scope for function variables, but you can also use it for loop variables. It's like, okay, I can do a lot of interesting things with this code block, right? Well, the code blocks are essentially concatenated together as if they are finite automata, or as if they are more sophisticated structures. We're going to combine these graphically. I think you know what we're going to do. We've already completed the renumbering, so now we're just going to put them next to each other. What's the first thing we did? We deleted one of the incoming start states, right? So that's gone, right? Okay. Now we're going to update the acceptance states. So what's the difference between these two slides? R1 and R2 go from accepting to non-accepting, as we expect. Okay. What's the next thing to do? I think we need to connect R1 and R2 to Q1. No problem. They were both originally accepting states, so it makes sense to connect both of them. We require no reading of the input string at all to go from R1 or R2 to Q1. We allow this to happen at any time. And non-deterministically, we just always happen to go to the second machine at the correct time. And this is it. That's everything. You just have to add those two little zeros in there.
Edges to the keyword.
Right, so this is never having two ones in a row. Only having two ones in a row.
I thought.
Yeah. This is not a great example because what this actually captures is that you can have either exactly one or more than one ones in a row. So this is the universal set. But it does show you how it works. And we can turn this back into a DFA if we need to. This thing has 5 states, so the DFA would have 32 states. And it would use all 32 states. This one will use all 32. And why is that? Well, I can be in this pair. 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 I guess that's not all 32, right? That's more. It's many more. Because you should assume at every point in time while you're in this DFA, you're always modeling this entire DFA as well. And so it is quite likely you're concurrently in all 3 of those states of that DFA. Yeah, actually, what is it? Okay, so there's 8 possibilities here plus just 16 possibilities, right? You don't need all 32, but you do need 16. You only need 16 because R1 and R2 happen to be mutually exclusive. So instead of having 4 possibilities, there you only have 2. Does that make sense to you at all?
Yeah.
Okay. That's what I just said. There's nothing particularly interesting here. This way of writing things is a little bit novel, but making sure we generate an edge that requires reading no input from all of the elements of the accepted set of first one to the starting state of the second one. Our last of the regular operations is the star operation. And I had to write star, because if you just put asterisk in a lot of typesetting things, it breaks, right? So you use it to mark down and it thinks you're trying to italicize something. This is slightly different. That's not actually an asterisk. That's a script asterisk in LaTeX. That's why it looks like that. So it's not up at the top. It doesn't have 5 sides. Do I have the markdown up? I can show you. I don't. It was cute. I really hate that this is what we use because to me it's so annoying to have to type it, but it sort of makes sense, right? It's like exponentiation without a power. Like, what else would you say, right? Okay. There's one wrinkle here, and really only one wrinkle. Most of this is quite easy. Because I think perhaps, I don't know where you're at cognitively with regards to this, right? But like an obvious thing to do is I say, well, I take all of my accepting states, and then I do an empty string edge back to the start state. And that's how I would run this thing multiple times, right? So the only thing we have to do then is deal with the case that you also have to accept the empty string. You also have to accept this thing runs 0 times. And so this is where you got to be careful about playing yourself. You're like, well, can I accept the initial state it's accepting? Well, no, not necessarily, because that initial state might be being used for computation, right? So there might be reasons that you're back in that initial state other than you're starting at the beginning of a list, right? So what we have to do is we have to add a phantom start state. And if you don't see why we have to have a phantom start state, a good exercise, I should be writing these down. I could assign these all to you for homework, but I don't know what I'm doing yet. A good exercise is to say, hey, what is one example of a language, not a language, of a DFA, perhaps, that models a language, it doesn't matter what the language is, for which I cannot set the starting state to be the accepting state and still have this property. And to me, the obvious ones are many of the examples we've seen where you get kicked back into the starting state when something goes wrong, but not necessarily at the beginning of the string, right? So, we're going to create a new queue. And what are we going to create a new queue? Well, we sort of teased this already. Basically, the only thing we need is we need our new fancy phantom start state that allows us to accept the empty set, or the empty string. And so we're going to accept the empty string. So we'll have an accept state. We'll have an edge out of that, that reads nothing, and that will go to our existing M1. That existing M1 will be unaltered, except every accept state will have an arrow back into the start state, but the start state will not be marked as an accept state, just in case. So how are we going to model that? We only add a new initial state. That's all. Star is very simple. Why is star so simple? Think about a while loop. Think about a for loop. If I have 1,000,000 lines of code in my for loop, to put it in a for loop requires 1,000,001 lines of code. One additional thing. That is your initializer, essentially. That's all it's doing. It's just initializing the loop. We need to support the empty string. Why is that? Many for loops run 0 times, right? Or they situationally run 0 times. I don't write that many if statements in my code anymore. I don't know what your experience as a developer was, but like, turns out I'm almost always either iterating or calling functions. I'm very rarely just doing an if statement, right? And I also do a lot of the obnoxious things with like using the ternary operator and multiplying things by Boolean result values. So a lot of things that are just conditionals I can write without an if statement, without control flow, right? We do need control flow for loops, so we implement it with Q0. Delta is identical, but we do have to add a few things. We're not stuck in the accept state, so we can keep going. One of the ways we can keep going is by adding paths back to the start state that don't require anything. So this is basically the same notion we used with concatenation. We're just concatenating something to itself. We have to concatenate to itself a potentially infinite number of times so we don't duplicate it. We just have arrows going back to the beginning. It's so clear looking at this to see how the early computer scientists realized they needed loops immediately. They're like, wow, we cannot do anything without loops. And they can't, but they have them. Right? So we go from Qn back to Q1. We don't require reading any empty string at all. Or we don't require reading any string at all, so we allow the empty string. And then we're also going to add one additional edge, and that's going to go from our new Q0, which allows us to accept the empty string. And that's going to go to what used to be the initial state. And that's to prevent us from accepting in the initial state if we're not supposed to. So we're going to add one edge each for the cardinality of f plus 1. This is what this looks like. This is how I wrote it. We take the old delta 1 and we take a union. Take the union over this monstrosity. So that is all Q2s that are elements of the accepting step. And then we also take it over Q0. And I hope that's not too bad. All right. All elements of the accepting step, Q0, boom, just call them all that. Perhaps you've written a list comprehension before, where you say like everything in this string plus one other thing. That's what we're doing here. Q0 is altered to the novel start state. Q0 is added to the accept states to accept the empty string. That's how we include the empty string. Let's do it. Okay, what's this doing? This is the 2 1s in a row. We are now going to allow any number of times it occurs that there are 2 1s in a row, right? It is more interesting to me to think of this as ending with 2 1s, and you just take this off. And so that means 2 1s can occur any number of times in the string, but you have to end with 2 1s, unless the string is empty. Does that make sense? Okay.
So
Any bit string that ends with 2 consecutive 1s. This is currently any bit string that contains 2 consecutive 1s. We change it to ends with by requiring nothing once we get to Q3. So if I see 2 1s in a row, and then a 0, I'm in trouble, right? Whereas that's allowed here. So how are we going to button this up? Well, we have one accept state, right? There's going to be an arrow from here back to here.
back to Q1.
And then we're going to put Q0 right here. This arrow will come into Q0, and there'll be an arrow that goes to Q1. All those arrows will have the empty string. We had Q0, and we know that it is accepting. Ta-da! What's that? That means nothing. We don't read a single thing. We do not care. Wow, I cannot believe I could highlight that. I assumed this was an image, and I just highlighted. Wow. Wait, what else can I highlight? Also, that one, I don't love this. That one is styled as subscript. You can check the source code, and you can also change it to not subscript, and it looks even worse. But that doesn't look like subscript at all to me, and it's supposed to be subscript, but that's just how it's stylized by this graphics language. See, like, to me, that's what subscript should look like, right? Because that looks like the zeros above the Q. Okay.
It's like power to Q.
Yeah, I don't know about that. Here's a reverse edge. Blue.
So if okay. Yeah.
Got it.
Q3 returns nothing. So wouldn't it go back to Q0 or Q1?
Goes back to Q1.
Q1.
Because it is important that it doesn't accept after that. So here is an example of something that shouldn't happen. We start here and we immediately transmit here. We see a 1 and then a 0. That should reject.
Okay.
So if this were an accept state, that would reject, right? Here's another thing that happens. We see nothing. We see a 1 and a 1.
Q3.
We imagine this isn't here because it's not helpful to us. We see a third consecutive 1.
Q2.
That should reject. Then we see a 0. If this is marked as an accept state, that accepts, right? So then we can say we're accepting 1, 1, 0, 1 with our machine that is only supposed to accept things that terminate with 1, 1.
Okay.
Yeah. It's like, oh, that's so contrived. What do you mean terminates with 1, 1? Well, like, here's an example. I am writing an optimizing compiler, and very often optimizing compilers run twice because they optimize all of the object files and then they optimize the executable. So your make file is supposed to check that you always ran your compiler twice in a row. Trivial. For years I used a LaTeX distribution that it had to run once to get all of the references, and then it had to run again to populate the bibliography. So essentially I was implementing in my mind this notion that I have to do 2 compiles in between every write. So the 0 denotes there's a more recent write than the last compile. 1 denotes there has been a compile. This captures how I manage my LaTeX files. This captures how I run my optimizing compiler, right? This is actually a practical thing to have. We just don't think of it in terms of 1. We think of it in terms of some property of the system. But we say, whatever system you're implementing, it has to adhere to this specification. All right. This is theorem 4. We have one type of graphical error here. Those are the same. Those should both be empty. 4, every language that is accepted or recognized by an NFA, or in fact any finite automata. There exists another finite automata that recognizes the star of that language. That language repeated any number of times, including 0. Want to be clear about how strong this claim is? This does not mean any member of that language repeated an arbitrary number of times. That means I can select any member of the language each time I repeat. So when I say all strings that end with 1, 1, I can do 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1. I can do all of those in a row and it will accept that.
I'm just confused.
So this is not multiplication. This is something else, something a little bit stronger. And there we have it. That's time for our stretch break. I'm going to take a bathroom break. If you are confused with something, you should work on that. Make sure you can accept the empty string transitions and what was the other one? Make sure you know how many states a DFA has if it's modeling an MFA. Those are the two things to think about. Or think about whatever you want, but that's what I would think about if I were you. I'm so thirsty. I'll need my computer or something. you doing? Any questions? The course this is based on gave 90-minute lectures over each of the 2 hours of lecture I give, and then had 1-hour recitations for each of those 2 lectures. So it's like the same number of hours. But I think like one of the things I was concerned about when I heard about the residency and all those things is I don't know anyone that like sits down and does all of this in 3 days. And so like if you get confused, we just need to like slow down. And if you're bored, we just need to speed up, and then I'll run out of material, but I'll just like start teaching you stuff off again. Sort of the way this works, right, is like at some point we're gonna say, like as I mentioned, like, and here's the pushdown automata, which is a generalized NFA that can also do these other things. And it's like, when that happens, like, there's no reason starting those lectures unless you feel pretty good about NFAs, right? And I think usually the way we feel good about NFAs is like, oh, you had your second homework on NFAs, we can see how you're doing. And this week it'll be like, how you doing? And then we'll just keep going, right? So, just communicate how you're doing if you get stuck on something.
There's like too much to process like for one time.
Yeah.
If there is any like video lectures or something that I can go back to, you know?
Yes, yeah. Absolutely, and I very highly recommend. Let's see if I can find them. They're linked from the website. That's the book. Here we go. Theory of Computation, MIT OpenCourseWare. This is the same class you were taking. The difference is I'm teaching it. These lectures are quite good. I am not going to play one of these videos for you because I got in trouble with YouTube last time I played someone else's video. But, right, so this is before lunch, except for non-determinism, which is also before lunch. We're right here, right? We're going to finish this up at 4:30, and then we're going to, no, this is at 4:30, and then we're going to do this right before we're done for the day. And then this is week 1, week 2. These are 3 hours of instruction plus a 1-hour recitation, and you've got 4 hours on this, so it's almost exactly the same. The problem sets here don't math very well. That's the big difference. So I think this problem set style made a lot of sense to that class, but I'm not totally clear. I think probably because we didn't all take the same like proofwriting class at MIT before here. I didn't feel great about giving you an assignment that says read and solve regular closure under perfect shuffle. I don't really know what that means, right? So I would rather give you something in Python that you can run it and see if it works. But that was the only change I was going to make. The textbook that this is based off of, which I have not read, because I don't read textbooks, it seems easy to find, so I just typed this in and it came up. And I'm assuming we're probably like encouraged to pay for a copy, but also like I don't think Professor Sipser doesn't know this is posted, so I don't like feel bad about it. And you can of course find a print copy if you would like. I'm assuming English is not necessarily your native language, so there could be a very good theory of computation textbook in another language as well that I wouldn't be aware of. But the theory will be identical, right? Unlike Python, which has the word for in it, none of these have English in them anywhere. And so many of the cryptography lectures I follow, as I mentioned, are written by people that don't speak English as their first language, and to me there's no difference. So that would be another thing to look into if you want. I just feel like as Americans we're supposed to think MIT knows how to teach things, right? So I toe the party line. What's the difference between an NFA and a DFA?
The difference between the NFA and DFA is set parameters.
Which parameters?
Okay, so DFA
Mm-hmm.
is like a string, like,
Yeah, perhaps. Keep going.
and this, I'm sorry,
No, it's okay.
let me make this up. Yeah, DFA is like the set of, the value of the set is like, in string, and the NFA, it's a set of states.
Yes.
Yes.
Yeah. Very good. Let me tell you what I think I heard you said it in my own words. In a DFA, I'll use the term specifically the delta function, the transition function. The return value of the transition function is a value.
Value.
That value is the state. And in an NFA, the return value of the delta function is a set of states. Yeah. Why does that matter? Well, I'm about to introduce another type of finite automata. This is the generalized NFA.
Okay.
The generalized NFA is not that bad, but it requires understanding not just NFAs, but one other thing, which is regular languages. The regular languages have union, concatenation, and star, which we've been reviewing, and then they are assembled from the atomics, letters of the alphabet, the empty string. I think that's it. They can also be the empty language. So, how's this work? Well, we're going to take an NFA, and we're going to say, well, instead of the labels on the edges for the transition function, the inputs to the transition function, being input characters, they're actually going to be regular languages. And this is getting very, very close to programming, right? I do arbitrary computation and then change the internal state of my computer. I do arbitrary computation and then change the internal state of my computer, right? Generalized NFAs are arbitrarily expressive at the NFA level, and so there's things that are very nice to write with them. So, the way we're going to do this is we've proved all the closure properties for NFAs and DFAs at the same time. We're going to prove some properties about the atomics. We're going to represent all of the atomics with an NFA. Then we're going to show that we can write generalized NFAs. And then we're just going to, with the closure properties, then we're just going to stitch them together. And essentially what we're going to show is given any regular expression, we can produce an equivalent generalized NFA. With any generalized NFA, we can produce an equivalent NFA. With any equivalent NFA, we can produce a DFA. And then DFAs and DFAs and regular expressions are the same thing, more or less. At the beginning of the day, I'm not going to quiz you on this, but I did mention the importance of keeping track of an automata, like an NFA, which recognizes a language, and a language itself, like a regular expression, which generates the language. So all these times, whenever I say equivalent, I mean the automata recognizes the generation. And with that, I believe in us. Okay. R here is denoting regular expressions, the set of regular expressions. Okay. Let's review things real quickly. For all NFAs, there exists a DFA that recognizes the same language. For any two NFAs, there exists a third NFA that recognizes the same language as the union. For any two NFAs, there is a third NFA that recognizes the concatenation of the language. We do note that order matters on concatenation, but not on union. That doesn't really affect anything. It just does. And then we note finally, yes, for every NFA, There's another NFA that represents the star of the NFA. Let's review regular expressions. And these will look quite familiar, right? We're getting them very close to each other. They are built from the atomics, one letter, any one letter in the alphabet. Usually for us that means 0 or 1, but it could mean A. It could mean OX. It could mean exclamation point. I used a Georgian script character in something the other day, just to demonstrate you can use whatever letter you want, right? Regular expressions can also be the empty language. And since we're building them from this, perhaps we take a concatenation with the empty language or something like that. That would be how we would use this. They can also be the empty string. A letter, the absence of a letter, or the absence of even the absence of a letter, right? True, false, none. Okay. And they are built from the same regular expressions we've been working with. Union. What's the next one?
Star.
That's 2 more.
No, disjoint.
Concatenation.
Concatenation.
Yeah. Which we use the disjoint set for. Yeah. Yes. Concatenation, which we constructed with disjoint union, among other operations, and the star. Yeah. Okay. Our goal is that we want to show that finite automata and regular expressions are equivalently expressive, right? So not that they do the same thing, but that they can capture the same ideas. The same notion of this is every prime number. Something like that, right? So the language that is a prime number of ones in a row could be generated by a regular, well, it can't be generated by a regular expression, or recognized by an automata. We do it with even number of ones in a row. So no, empty string 1 1 1 1 1 1 1 1 1 1 1 1 blah blah blah. So we can do both of those. Okay, we recall what closure is. A closure is when we have a set and some operation or relation over that set. Those are the regular operations. And we know, again, our example, addition is closed for the natural numbers because any 2 natural numbers added together are a natural number, and subtraction is not. So we need to make sure we're not subtracting. We need to be careful because addition and subtraction look an awful lot like the same thing to me, so I never want to cheat here by accident. Okay, so we're going to work with numbers, or with languages. Okay, we're going to show that we can turn a regular expression into an NFA. How are we going to do that? Let's begin with the atomics, first of all. Okay. So we need to deal with all of the atomic cases. These atomic cases are the letters, the empty set, the empty string. And we're going to begin with showing letter atomicity because this is the easiest one. I hope you can imagine in your mind that it is not very difficult to write an NFA that accepts a string of length 1 that contains a specific letter. Think about how you would do that for a moment. How many states would you have? What would the edges be?
I have 4 states.
Why do you need 4 states? What are the 4?
Q0 to.
What does Q0 represent? So Q0 is your initial state, right?
Initial state represents 0 and nothing.
Okay, that represents nothing. Okay.
And then we go to 0, we have to Q1.
Mm-hmm. Is that edge labeled? The edge from Q0 to Q1?
No, I think it's not.
Okay, so that's an empty string edge. Okay.
And then if it's 0,
Mm-hmm.
then it will reverse 1 Q1.
Okay.
If it's 1, we'll go further to Q2.
Okay.
And then I think it should be
And then what language does that represent?
M1. I think it doesn't matter with the language. It can.
Yeah. So I'm going to ask you to create, or to envision, and you can write it down if you'd like, a DFA that accepts exactly this language. It is the set that contains only one string, and the string is 0. A string of length 1 of exactly 1 character, 0. How do you create that NFA?
So I have DFA.
Or NFA, any finite automata, yeah. I just opened Python. So we're going to say the L of M, we'll call this M7, just because we haven't used that number yet. What is M7? What is the machine that accepts exactly that one character? And so we'll recall that M7 is going to equal the tuple of a set of states, some alphabet sigma, some delta function, some Q naught, and some set of states F, right? What are each of these things?
So what's the main question? Will it be written, or what kind of?
What would the machine look like? I would imagine the machine graphically, but how would you express a DFA that accepts the singleton string 0, the string of length 1 that contains only 0? It must reject all other strings, and it must accept precisely that string.
Must reject all of other and accept only this.
Yep. If there's 2 zeros, it rejects it. If there's a single 1, it rejects it. If it's the empty string, it rejects it. It has to reject in all other cases. I'm going to grab some water. Think about this for a minute. Don't overthink it. It's not a trick question. This is the type of thing I'm asking for, right? We can cheat and use Python double equals, right? If we had to do this with the DFA, we could do it as well.
It can replicate any language, right? Doesn't
Wait, sorry. Any language? What do you say?
you're asking there what language?
I'm asking, write a DFA that accepts the language LM7. That language is a set of strings. Which is how we can define languages. An example of something that is not a DFA that recognizes M7. LM7 is lambda expression. That's not a DFA. Because it doesn't have 5 components of a DFA. Big Q, big sigma, delta, Q naught, and F. You recall when we showed I wrote a machine that could accept the has key once in a row and the dictionary, and we could look up different strings in the dictionary that those some different ones in the row at the end. You remember that? Maybe a helpful way to think of this is perhaps like how many accepting states should you have, and what should the arrows into those accepting states look like? Oh yeah, you can use whatever you want. The answer's on the next slide, the following slide. Oh, I didn't tell you my AI policy. You can use them. I use them like a little bit besides. So once in a while I'd be like, hey, can you turn this language into a different form of this language? It didn't seem to be able to do it. I don't think you can do this stuff. So you can ask AIs. But I even had the experience where I like asked it for something once and I was like, that's obviously wrong. Like, can you tell this is wrong? And it's like, oh yes, that thing I just gave you is wrong. And I was like, can you fix it? And it like gives me the same thing. So I had, I don't know what you'll find. This is, yeah, kind of formal mathematics, so we're really looking that up. I think the next slide is Alright, I'm going to ask you questions while you're doing this. I hope that it's helpful for both of us. Alright, what are you working on? Yeah.
First thing, Gemini.
Yeah, this let's see.
So it says, first take string from the candidate. It starts with 0, right? And it will go to M7. Return true, or 0 is in language. It will return, I don't get this. Because M7 is 0 is true, 0 is added to the LM7, right?
Yeah. So, because the
Wait, this is where I have to.
finite automata between M7, when it reads the string 0,
Yes.
it accepts the string, so it returns
True.
true. And this is how the finite automata are functions from bit strings to bits. 0 is a bit string. It is the only bit string that maps to 1. Everything else maps to 0. Did that help?
Still trying to figure it out.
Are you good with the DFAs taking a bit string and returning a bit? Does that work for you?
This is very good.
So I think in Python or another language, right, we would feel comfortable creating a function that returns true if the input is 0, or returns false otherwise, right?
Can you explain this? I'm lying down right now.
Yeah. I'm going to go right to Python about this. So we don't have to think of a finite automata as a function, but we can think of it that way. So I can create something, and we can call it perhaps M7. I selected 7 arbitrarily. It can be anything. It could be MN. It can be just M. Doesn't matter. It accepts some string, S, which is of type string. I could equivalently argue it should be of type int, because they're bit strings, which are either numbers or strings. It makes no difference, right? And this is going to return, we usually say a 0 or a 1, but we can also say it returns a Boolean. It makes no difference, right? So I asked, can we write the function that accepts the string 0 and rejects all other strings? We can do that with an if statement. S is equal to 0. Return true. Else, we return false. That is one way to think of this, and I will demonstrate that this works. If statements are relatively close to the paths we take, so we can think of this as our input state. We can think of this as reading the first letter. We can think of this as an accepting state, and this as a non-accepting state. So I can draw out the automata the same way. I'm going to rewrite this to be more concise. This statement is either true or false, right?
Yes.
So I don't need to return true and false. I will simply return S equals 0. going to draw this. The first thing I will always need in all cases is a start state, which will denote Q0. Q0 will always have some incoming edge. I want to return true or accept if I see a 0 and not otherwise. So I'm going to have an edge labeled 0. And it's going to go to some node. If I see only 0, I should accept or return true. How do I denote that I accept on one of these finite automata?
Okay, it has edge next.
Because of this edge?
Yes.
Okay. Does that edge correspond to acceptance or something else? There are the 5 components. There's the states. There's the alphabet. There's the transitions. There's the start state. And there's the accept states. Which one of those 5 things is represented by an arrow? Acceptance is represented by an arrow. There's 2 arrows up here. Which one of them represents acceptance?
From Q0 to Q1.
Okay.
Because the first arrow represents start.
Okay. Say I additionally have this arrow. Oh dear. Oh my gosh. My mouse lagged. Okay. Okay. Now what represents acceptance? This is a letter in the alphabet. This corresponds to sigma. This arrow connects a state to another state, depending on the value of sigma. The combination of a state and a sigma going to another state is exactly what delta is. These arrows are exactly the delta functions. This is Q0 cross Q1 returns Q2. This is Q0 cross 0 returns Q1. These are internal functions of the automata. We do not determine whether it accepts or rejects. The way an automata denotes an acceptance state is with a double circle. Which we've usually shown like this. Right. Do you remember seeing these double circles? So this denotes that Q1 is a member of the set F. The set F is the accept state F for finish or final.
Accept.
Yeah. So this automata, and it does not matter if this is here or not. It has no relevance. If you see a 0, you accept, and you not accept anything else. Because if you see a 0 then a 1, there's no transition here, so you have a failure. If you see a 1, you go here, which is not an accept state. Another way to stylize this anything you read from Q1 causes a rejection going to Q2. And if we ever go to Q2, and I have the wrong paren on one of my edges there, I'm sorry. If we ever go to Q2, we will never accept. If we ever read a 1, we will never accept. If we read a second 0, we will never accept. But we don't actually need any of that. It is sufficient to say, starting in Q0, read a 0, then accept. Otherwise, reject. And the logical equivalence of this is return x equals 0. And specifically return x0 equals 0 and length equals 0. And this is return x0 equals 0, else return false. This is else return false.
This is else.
We don't need that on Sprinch. Just going to paste with no background again, but I can't do anything about that. Who's this? I don't know who that is. Okay. So, if we have an atomic single letter language, we need two states. We need an initial state, which is not accepting, because we haven't read the letter yet, and an accepting state, which is accepting, because we read just full. Our delta contains exactly one arrow. The arrow that conducts us from the non-accepting to the accepting state, which does so only and exactly once, and it reads the correct letter. Anything other than the correct letter is undefined, and therefore bad. So if we see the letter, we go immediately to Q. Yes. And the accepting state is Q1. We do not care about sigma at all for this, because we're only looking for one letter. It doesn't matter what the possible letters are. So that could be any character. It could be exactly these characters. We might just be measuring the length of a string. We don't care.
You don't care about the letters.
Yeah. And we don't particularly care about the start state, right, because there's only one. So this is how I denoted it. To do a mapping, to me, Q is the set of Q0 and Q1. It is the set of nodes. Delta is the set of labeled edges. And then F is the double circles. Final, finish, whatever. Yeah. Empty string atomicity. This one's not too bad. We're going to do pretty much the same thing. All you have to do, so you have to accept if there's no characters, which means you have to reject if there's any characters. So we need an accepting state, and it can't have any characters that it's read.
Nothing.
And what's the place we are when we haven't read any characters yet? The initial state. So we set the initial state to be the accepting state. So what are we going to do? We're going to create...
Initial state will be the empty string, right?
Yes.
Oh, okay.
Because we're trying to accept things. We're going to create a machine that accepts such that the language accepted by the machine is equal to the empty string. There's going to be exactly one state, the initial state. There's going to be no arrows.
Data. No,
Because if we read an arrow, we reject, right? So any arrow would just be reject. If I see an A, I'm not going to return
false.
Yep. The accepting state is the same as the initial state. That's it, right there. If I read any letter, it rejects, right? But if I don't, right, next one, empty language atomicity. We have to return false no matter what. Very easy. How do we return true? With an accept state. So we simply set our accept states to the null set. With no accept states.
So there will be no accept state.
Yep, that's all. It does not matter what you do other than that. I'm going to show you the minimal example, right? But any automata where f is the null set is returning false.
So there will be no delta or.
You don't need them. But also, it's even stronger than that. It's no matter what delta and sigma are, it still returns false.
No matter what. So
Yeah.
it will always return false.
Yeah, it will always return false. I need one state, but I can also accept any infinite numbers, or any finite number of states, because if I have infinite, it's not a DFA anymore. But any finite number of states, as long as none of them are accepted. Doesn't matter what delta is, I don't care. Only matters.
Final states.
Yes, there are no final states.
But final states and then overs. Okay.
Yeah.
Right.
This is, I can give an example. I'm going to call this empty lang. And I'm not even going to return a Boolean. No return statement at all.
Pass.
Yeah. Let's look at the Boolean value of this. Might as well be false, right? False. I don't have to put a language in here. Put in numbers. I can put in another function. No matter what. We're just getting false. We're not getting true back. Right? Okay. So that's empty language atomicity, empty string atomicity, and letter atomicity. Right? This is the minimal one, but you can have any of these if you want. If you want 10,000 states, I don't care. I refer to this as the atomicity lemma. I don't think it was labeled in the book. I wanted to put it all on one slide. But what does this represent? If I have a single letter language, a zero letter language, or a null set, an empty language, a language that contains zero strings. This is the string of length 0. That is the set of size 0. I can construct each of these fairly straightforwardly. This is wrong. I should say Q0. Because it's the same, right? I only have one set, one state.
Oh, I did.
It must be the acceptance state. Okay. All right. With the benefit of the atomicity lemmas, which we just went over, and the closure properties, which we went over as well. Perhaps before lunch, some of them before lunch, some of them after. We can now show that any regular expression has a corresponding finite automata. We're going to do that by basically combining things together until we get to the finite automata, right? So how are we going to do this? For composite R, what can it be? Well, it can either be some other R or some other atomic, doesn't matter. And then they're going to be combined by union, concatenation, star. So we've proven this over NFAs. We had used theorem 2, which was that NFAs and DFAs are equivalent, but we did prove that. right, by using a lot of states. We showed that union is the same by showing we could execute non-deterministically. We showed that concatenation is the same by showing we could execute serially, one after the other. And we also had to do that non-deterministically, but that wasn't a huge deal. And then we showed star works by doing the special initial state, and then doing the loop from the accepting states back to the start state. Okay. And by the way, the proof of star included the way to generate the DFA that returns, or that only accepts the empty string, right? Because we basically wrote that DFA, and we concatenated it to the other DFA. Okay. Here's Theorem 5. Theorem 5 is more complete. It is that for all regular expressions, which are made over the atomics and the operators, there exists a machine which has states and edges, such that the language accepted by the machine is the same as the language generated by the expression. Okay, how are we going to prove this? Well, we already did. By atomicity, we have the atomicity lemmas. So if this thing is of length 1 or 0, or contains no strings, we've already proven it. And if it's composite, well, then it's composite over the things we already proved and closure properties. So we simply use our closure properties and we apply them. Any regular expression is made out of the same things that we have closure for on our DFAs. So therefore we're all good. Oh, I missed my little box. I usually put a box at the end of my proofs. It doesn't have a QED box. Have you seen that? Where you put like a little black box at the end of your proof to denote it's over and it's shaded in? I love those things. Okay, we're going to do generalized NFA. Okay. We can understand delta as a transition relation. What does that mean? Well, we've shown that single letters are themselves regular expressions by definition, right? And that singular letters still constitute DFAs or NFAs, right? So what that means is that actually we're already putting a subset of regular expressions on our edge labels. It's just a very restricted subset. But there's not actually anything that's restricting us from not saying, well, actually, this is the A star edge. Follow this edge if you read a bunch of A's in a row, or perhaps 0 A's, any number of A's in a row, or any number of zeros in a row, right? We can define that in our transition function, right? For DFAs and NFAs, these transition relations are deterministic, including for the NFAs, because what the NFA is non-deterministic over is whether it needs to be in the accepting state, not over how its actual transition relationship works, right? The only difference is we've only accepted certain things for edge labels. We've only accepted elements of sigma for edge labels. But elements of sigma are all regular languages, by definition. So let's just put any other regular language there. So we're not just going to say the letter is the element of the label. We're going to have transitions that think. These are going to be transitions that compute. And the thing they are going to compute is whether some substring they read from a larger string is consistent with a regular language. Okay, so instead of identity exclusion, we're going to put regular expressions on the transition labels. So it is completely legal for me to say A star union B. I'm allowed to put that on an edge label. Do you think that's thunder? It doesn't look that stormy out.
Yeah, it is thunder.
It's thunder? Okay, all right.
So I saw the light. Oh, it's raining.
It's right. Okay. Great. Okay. We have to walk out now. Oh, we don't need to talk about this now, but think about what you need to do for dinner, because I think I'm your ride. So just think about it. I don't know if you're going to grab some Indian food and like take it back to the hotel or whatever you want to do. But just have a plan. I'll ask you at 5:30. Okay. So A union B star. That is completely legal. A is an atomic, B is an atomic. Union is a regular operator. So that's a regular operator over a regular operator over 2 atomics. I just put it on my edge label. No problem. Why wouldn't that be allowed? I don't know. We should probably prove that we can do it now. Let's demonstrate. So how are we going to implement this? Every operation can be an NFA. You have closure. Any NFA node can be replaced with an MFA because we've shown concatenation. We've shown we can stitch these things together. We can hook them up and plug them together. We did that with both concatenation and star, right? These are essentially the closure options. So a GNFA is equivalently expressive to an NFA, but it might require many, many fewer states. That's your problem if you don't understand this. You have to go figure it out yourself. Proof's in the book. It's not that hard. Essentially, you have to do the thing we did with concatenation with arbitrary nodes, but that's all. So instead of putting one DFA after another, you have to put a DFA in the middle of another DFA. That's sort of what we talked about with function calls, right? Okay. We're going to restrict ourselves to a special form of GNFAs, which we're also not going to prove, but you can prove, and it's not impossible. They're all going to have a single accept state that just makes the math easier. It has actually been extremely annoying this whole time. We've had a set of acceptance conditions, right? That hasn't helped us at all. And then you're going to have connections to all states, except what? The start state is not going to have, what is it? The start state is not necessarily going to have an incoming state edge from the end state. And the end state, the acceptance state, is not required to have outgoing edges. So if we have 4 states, they're all connected. Each state is connected to all of the other 3 states. That's all. And how do we deal with that? Well, if there's not supposed to be any edge there, we just put the empty language on there, and then absolutely nothing can go along that edge. So what this means is we now get to assume there's edges or not. You always have an edge if you need one, and you can say there's an edge between any 2 states, even if it's the empty language edge. Okay.
But there has to be a connection between the initial state and the final state.
Mm-hmm. And if you can't just accept initially, then you simply say, oh, that's the empty language. There is nothing that allows you to accept immediately. And if there's something that allows you to accept immediately, well, then that's the language that goes on the edge. Okay. Right. It is important to specify GNFA, if there's not a label there, that refers to the empty language. Whereas in NFA, if there's not a label there, that refers to the empty string. This is ludicrously confusing. I don't know a way to make that easier. But just be aware.
GNFA is empty language.
Yeah.
NFA is the empty string.
Yes, if you have an empty edge, right? And I've tried to show this. So whenever I've shown you NFAs or any kind of finite automata, so I always put the labels in a set. That's because those are sets of labels. They're not quite languages yet, right? So, all right. Let's go from an NFA to a regular expression. Okay, so how are we going to do this? For all M, DFA, NFA, GNFA, doesn't matter. There exists an R, regular expression, such that R is the language recognized by M. Okay. We're going to use a GNFA. G. We're going to use induction. Are you comfortable with induction? Okay. I might have to teach you induction then. We'll see. I've referred to the notion that the sum of any 2 natural numbers is itself a natural number. I can prove that with induction. I'm going to say it out loud and we'll work through it if we need to. 1 is a natural number. If I add 1 to 1, I get 2. That's a natural number. So what that means is that if I add 1 to a natural number that is 1, I get 2, right? We can proceed inductively, we say. Well, what if we add 1 plus 1 plus 1? Well, 1 plus 1 we know to be a natural number, and we know 1 to be a natural number. So any sum of natural numbers is a natural number. So we say for all n plus 1 is a natural number if n is a natural number. Okay? And then separately we say 1 is a natural number. And then we say, well, every natural number is some number of 1s. Therefore, they are all part of addition. And why doesn't this work for subtraction? Very easy, right? Is 1 minus 1 a natural number? No. Okay. So it's the notion that you have a base case that you can prove and an inductive hypothesis, which is if something is true over n, is it also true over n plus 1? We can often prove that. And you prove them together. That gives you the full proof. So what we're going to do is we're going to do induction. We're going to do, our base case is going to be the atomicity lemma, and then our inductive cases are going to be the closure properties. Okay, here we go. Right, it is very helpful that we can measure how big automata are in some useful way, which is that we have the size, we can say their size is equivalent to the number of states. Because we're using GNFAs of general form, they all have the same number of edges if they have the same number of states, because we have an edge between every state. So it doesn't matter. We don't worry about it at all, right? And they all have the same number of starting states, and they all have the same number of accepting states, 1. Okay, so we're going to begin. How do we begin? We're going to use our simplifying assumptions. Our base GFA has 2 states. What are the 2 states? The start state and the accept state. What are they connected by? They're connected by 1 edge, and that edge has the name of a regular language on it, because that's what we're labeling our edges with that. Okay. Start state, end state. I should call it the accept state. I should call it the final state. Okay. On these slides, I'm going to use the shorthand that if I put cardinality on a machine, I'm referring to the number of states it has. I'm not referring to this fact that it is a tuple of length 6 or 5. I don't know how you count. So just be aware of that. Okay. So here is the base case. We have a 2-state GNFA. We're going to call it G. It has an initial state, Q0, and an accepting state, Q1. And its edge is labeled with R. What is R? Any regular language.
Any regular expression.
Mm-hmm. Yes, any regular expression. So that can be the empty language, in which case this accepts nothing. That can be the empty string, in which case this accepts exactly the empty string and nothing else. And that could be any other language as well, in which case it accepts exactly that language. So, what does this mean? Well, not too bad. By definition, in order for something to accept, it begins in the initial state and ends in the accept state. By definition, the only thing that can cause us to go from the initial state to the acceptance state is the language itself. We just label whatever that arrow is with whatever language we're trying to show equivalency to. So what this means is that every GNFA that is of minimal size, which is of size 2 states, is necessarily equivalent to a regular language. And which regular language? The regular language of its edge label. Okay? Let's look at a more complicated GNFA. What do you say? Okay. So, oh, there's my box. See, I missed it earlier. All right, it's back. Yeah. Okay, induction. Okay. So, say we have a GNFA that has k states, and k is more than 2. Well, we need to get rid of one of the states. And I know just the trick. I'm going to fiddle around with delta. Because all of those arrows, I can make them go somewhere else, right? It's actually fun to be calling this delta, because Delta Airlines is the big thing around here, and we're talking about connections. I just thought of that. Okay, so we've got a GNFA, and it has more than k states, and we're going to take one of the states out. And when we take all of those states out, we can almost think of like as if we're holding the edges. And we just take all of the edges and we hook them up in such a way that they satisfy all of our requirements.
So we set edges in a way that it can
right.
Convert from 2 states to from 1 state, right?
Yes. And the reason we can do that, thinking ahead, those edges have regular languages on them. and I can concatenate regular languages. And so let's go through the steps. I think it's a little bit easier to see it this way. Okay, we're going to prove our theorem. We asked if we needed to go over induction. I think we went over induction. If you're not familiar with induction, that's your problem. Okay?
I'll do it.
Yeah. It's not bad. And I would rather you find materials on induction you're comfortable with, because it's not like specific to this. So like if you find a good YouTube video on induction, that makes sense. I don't think you're going to find a good YouTube video on generalized non-deterministic finite automata, but you will on induction. Okay. So we're going to do a process called state exclusion. What are we going to do? Given a generalized non-deterministic finite automata with k states, where k is more than 2, I'm going to pick any state. Doesn't matter which one. It will work for all of them. I'm going to pick any state that is not the start state or the accept state. And that is going to be my state, and I'm going to denote it Q1, or Qi. That's not a 1. Okay. Q sub I. It's just the name of a state that is not the start state or the end state. Okay. Then I am going to go look at delta. I will note that delta will have a number of edges that are incident on, that include Q sub I. I'm going to look at all of those edges. I'm going to specify them as follows. I'm going to let delta sub I, comma 0 be edges that come in to Qi. Those are edges before Qi.
Oh, so it's like initial edges.
Initial edges, but also edges from any other state. Remember, every state is connected. We assumed that,
Oh.
right? So every single other state has an edge that goes to my state, Qi. So I take all of them. Okay? I wonder if there's a... No, that's fine. I think that's good. Okay. I'm going to do the same thing with edges going out of my state. So my state was required by law to have an edge that goes to every other state. No trouble at all for me. I'll take all of those states and I will call it delta I1. And I just have to call it something, that's why I'm calling it this. Okay. So, my state is the destination of I0 and the source of I1. This is every other state, this is every other state, because these are all sets. Okay? What am I going to do with this? I'm going to additionally note, and I forgot, these things are allowed to have edges to themselves. We've seen this before, the self edge. So I'm also going to grab the self edge. And that self edge is going to, maybe it's going to be the empty language and there's not a self edge. Maybe it's going to be some very complicated regular language. It doesn't affect me.
So most of them have a self edge, right?
Yes. I think they're all required to have a self edge. I would say.
All required. Yeah, that's what I was asking.
Yeah.
They all have a self edge, or most of them have?
Yeah. All of them. We
All of
require
them.
them all. Every state has an arrow to every state.
Every state
And every state is every state. So they all have an arrow.
Okay.
And you can also just like say we don't allow self edges if you want, right? I did. So I also have S, which stands for self edge. Okay, what am I going to do with this? Well, I'm going to build a new delta. I'm going to take the deltas I had previously, which are these ones here that I pulled out, that I yanked out. So I'm going to take the union over them. I'm going to remember there's an edge between all nodes, except when we deal with special cases with the acceptance state. And I'm going to add new transitions. Okay, so I'm going to define a new transition. I'm going to say Rij is the language on the edge from state I to state j. That's just a way of referring to the edge label. Okay? If I go from Qx, state x, to state y in 2 steps, or I guess not necessarily in a step, by passing through QI. QI is the node I'm trying to remove, and I'm trying to go from QX to QY.
Okay.
How do I do that? Well, in order to get to QI, I'm going to go from X to I. While I'm at I, I'm going to go from I to I. And then to leave I, I'm going to go from I to Y. That's a regular language. This is a regular language, that's a regular language, that's a regular language. I'm allowed to concatenate regular languages. So no problem. This is still a regular language. Okay. There is one thing I have to remember, though. This is a regular language that transmits me from X to Y. There's already a regular language that does that, called RXY, the label of the arrow from X to Y. There's already an arrow there. Oh no, what do? No problem. The union of this and that is also a regular language. And you see now why we proved star, because I can do this a star number of times. Concatenation, so that's a concatenation. And union, that's union. These RIIs should have stars on them. It doesn't really matter. So I'm going to have a new edge label from X to Y. What is it going to be? It's going to be the existing label union with RXI, RII, RIY. That's all.
Next to II, II, II again. And then Y.
Yep. All of the things I could have to read to go from X to Y if I pass through I, or any of the things I can read to go from X to Y without passing through I. That's all. Then what am I going to do? I'm going to construct a new delta, and it's only going to have these things in it. There will now be no edges that go through QI,
I.
because I took it out.
You go from X to directly to Y.
Yep. And I just change what I have to read if I was previously going through I. Okay? That's the inductive lemma. It's not that bad. It's not that good either. Let's do it graphically. Imagine k equals 3, q0, qn, which is our intercept, and qi. R, S, T, B, those are just names of languages. I have to call them something, so I call them R, S, T, B. I take out qi. I just imagine it's gone. That's all. It's just a thinking stage. What am I going to do now? I'm going to remove the edges that were incident. So the way I denoted this is I took out all of the edges and I put them over here. I still have those regular languages. I'm holding on to them. I know what they are. And they're called R, S, and T. I add those edges back in, R, S, and it should be S star. Doesn't matter. R, S, T, right? I am required by law to only have one edge. So I'm going to combine those two edges. A little thing I like to call union. And this is equivalent. It accepts all the same strings. And it has one fewer state. Which means I can always take out any number of states until I get down to 2. And when I get down to 2, that is the regular language that the automata accepts. So that's how we can take any given regular language or any given finite automata and turn them into each other. And that's how I write this proof. By induction, I say. My throat's killing me, so we have to take another break. Let me see what's next, though, before we stop. Read up on induction if you're stuck. Okay, that's regularity. It's, I don't know what time it is. It is 3:46. Okay. I'm gonna go find a drink. See you soon. I might even buy something. I'm not desperate. All right. Let me give you a little more context too, because sometimes that helps. Also, I'm just sitting down because I'm tired of standing up all day. Why are we doing all of this, right? We want to show there's questions computers can't answer. This pumping lemma is the first example of something an automata can't answer, right? So we spent all this work building up DFAs so we can show there's something they can't do. And when we're done with that, we're going to build the next more powerful thing, and we're going to show there's something it can't do. And then we're going to build the maximally powerful thing and show there's something it can't do. And that's sort of how computability theory, I don't know, is operationalized or like is used or is appreciated. It's like, here's the things we can't do. And then complexity theory will come in over the next thing, like, here's the things that take a long time but are possible. So, if we've sort of got our heads on straight about DFAs, this is going to be a way to show, here's a way I can take a language, and if it can't be recognized by a DFA, I can prove it. And you prove it with this thing called the pumping lemma. And there are two pumping lemmas. There's one for deterministic finite, or any finite automata, and there's one for context-free grammars, which is the next thing. So, in terms of today, the hope is, at the end of the day, you basically understand what a DFA is, and you understand a way to show there's things they can't do. And then I give you enough of context-free grammars you can sleep on it and feel a little better going into tomorrow. So that's the plan. That's what we have left for today. In theory, there's 2 hours of lecture left, and I'm just going to stop talking at 5:30 because I won't be able to talk anymore, so we'll see where we are. Yeah, does that sound good? Do you want to ask any questions before we go?
What? I can.
Yeah.
We'll start.
Just go for it?
Yeah.
Cool. What's a DFA?
Sorry?
What is a DFA?
Definite.
Yeah.
Deconstruct.
And how do I define it mathematically?
If it has state has
Yep, there's a state. Okay.
has nothing value.
Yes. Uh-huh. What else does it
Right.
have?
And then just
It's a 5 tuple,
5 to yes.
right? What are the 5? States? You said that
States.
one. What's next?
Lambda.
Sigma.
Sigma.
Yeah, the letters. Yep.
Sigma.
Yeah, yeah.
Acceptance.
I have that one last, but yeah, acceptance. F.
And I don't.
Yeah.
And
I just have to do them in my order, so I remember.
Okay. Language.
Languages are different, right? Languages are recognized.
States.
States, letters,
Letters.
delta. What's delta?
The arrows.
The arrows, right? So I got nodes and edges,
Nodes and edges.
if we think of it as a graph. And then if we draw it out, you've got circles and lines.
Circles. That's the states.
Yeah. The circles are states and the lines are deltas.
Deltas.
And then the last thing is the initial state.
Initial state.
And what they do is they take a bit string and they return true or false.
True or false.
I'm going to show a way of describing a bit string that a DFA would not be able to return true or false. There exist bit strings that I can write down and describe precisely that a DFA cannot use to describe. I'm going to prove it. That's the pumping lemma. One of the only, I think, like to me, lemmas that has like a name that like describes what it does. So I'm used to things like, the fundamental theorem of calculus. It's like what that, it's like the name has nothing to do with what it is, right? I've just been numbering my theorems so far, but I use the atomicity lemmas. Remember those? I try and name them when I can. Preface. Avoid this trap. Wait, okay, sorry. Pumping lemma. Statement lemmas. Okay. Suppose we wish to prove a language is not regular. This is what everyone always does in undergrad. Maybe you did this in undergrad, I don't know. So we say, we have to prove there's no DFA that recognizes the language. And you also say, I know. I'll think about it really hard, and if I don't think of the language, that means there isn't one. That doesn't work. You can't write as proof, I thought about it really hard and couldn't think of one. So we're going to think about it really hard and prove there isn't one. And it's going to be much harder than thinking about it. So don't do this. Don't say, I couldn't find the DFA, therefore there must not be a DFA. Because there's some really weird stuff that DFAs can describe and not describe. Here's an example. We're going to take sigma, which for me is the second of the tuple. And we're going to say 0, 1, because for me, DFAs take bit strings into bits. Okay? We're going to say B is the language for which there are equal numbers of zeros and ones. You can think about it for a minute, and you'll be pretty sure there's no way you can write a DFA that does this, because DFAs don't have counters. And the way you would usually do this is with a counter. You would count your zeros and your ones. And then you think, oh, I don't need to count the number of zeros and ones, I can count the difference. And you can't really do that either, right? And because this is any finite number of zeros and ones, if you start using states to count, then you need any finite number of states. And so now you need as many states as the length of your string can be, right? So we get into a problem there pretty quick. Here's another one. Here's C. C is the language for which there are equal numbers of 0, 1, and 1, 0. This is kind of goofy, because that thing's not in C. And this thing is, right? And that feels a little weird to me, right? One of these is regular. Good luck. You can figure it out.
So one of these is regular.
Yes. Do you know which one?
Yeah, first one.
Okay. If you're sure, write that down and we'll come back to it later. Okay.
0, 1, 0, 1.
Oh, so these are strings, right? These are not. This is not a language. The languages here are B and C. A string cannot have the property of being regular, because regular is a property of a set of strings. Languages are regular. Strings are members of languages. So a string can be in a regular language. We always want to keep distinct the difference between sets and the elements of sets, right? A machine accepts a string and it recognizes a language. A grammar can produce some string and describes an entire language. It is non-trivial to conclude which of these is regular, so we're going to find a proof technique to do so. And specifically, we're going to demonstrate whether B or C is regular. The language for which there are equal numbers of zeros and ones, or the language for which there are equal numbers of 0, 1, and 1, 0. Okay, pumpkin lemma. For all languages, which I denote A. Why is it A? That's the capital lowercase a, and I use lowercase a for letters. So that's where big A comes from. For all languages, there exists some natural number value, which is the pumpkin value. This E corresponds to the pumpkin. Okay? Such that there exists X, Y, Z. That is a string, because it is an element of A. X, Y, Z in A, such that the length of X, Y, Z is greater than B. There is some value, but there is a set of 3 substrings that is larger than B. And given this, for all natural values, X, Y, to any number. So this is essentially xy star z is an element of the language. Okay? String that is element of the language, another string that is an element of the language. These are strings, these are set elements. A is a set. That is a number. Set, string, or number, set, number, string, set. There we go. I was backwards. Set, string, number. Okay. Take another number. This doesn't matter. That just means y star. We don't care about that. These things are all part of A. Okay. And also we have the case that y is greater than 0 in length, because this is trivial if you just put the empty string in there. It doesn't help us at all. And then we also have that x and y, sort of the prefix, are less than the function length. So essentially, the length p is somewhere inside this v. Now, it doesn't really matter what that is, because we're going to pick x, y, and z anyways. We're going to use that for notational prefixes. So that's what we're going to do. There's some prefix that is less than p. It contains a subset that is of length greater than 0. That we can pump. We can include more than one time. Okay. xz, xyz, and xyyz are all elements of A. I want to update this statement to include star, so I'm going to note that yourself. Update statement to include star. Okay. All right. Oh, my throat always hurts after I fly in airplanes, and I'm not used to flying this far. I bet it's not the talking. It's probably being on the airplane for 5.5 hours. I was like, what am I doing wrong? Like, no, I didn't do anything wrong. I got on an airplane. Okay. We're going to pump up the number of occurrences of y. I don't know that occurrences is spelled correctly there. Okay. So, let's reiterate. There exists some machine, some deterministic finite automata. Its language is A. We're going to let P, which is the number that we know exists, it can be any natural number, we're going to set that to be how many states that machine has. So, the number of states, the cardinality of the set of states. Every time we were up on the board, I was like, how many states are there here? Remember? We're like, oh, there's 6, there's 5, non-deterministic ones have more. That's what we're talking about. One of the niceties of this is, since I'm working with natural numbers, if I guess too high or too low, I have lots of numbers to work with, right? The only thing is it has to be higher than the number of states, because what I'm going to do is I'm going to show I'm going to repeat a state. So it has to be more than the number of states. So I have a string longer than my number of states. All the examples we've worked with are like this, right? So you remember the contains 2 ones string? That was a string of length 5, and there were 3 states. No problem. Okay. So I'm going to take S, and I'm just going to say S is the name of the string. And S is the name of the string that upon which I am going to pump, right? So X, Y, Z is S, string S, such that S is greater in length than P, which is equivalent to the number of states, right? So S is longer than the number of states. That's all. Okay. Sketch of proof. Okay. Every time I read a letter, I go from one state to another state. Sometimes I stay in the same state. That doesn't matter. Which means that if my S is longer than my number of states, I will necessarily repeat a state once, right? Because I will run out of unique states to visit. If there's 50 states in the United States, right? If I visit 51 states, it means I visited one more than once. Same idea. Don't know of a good example other than that. 14 provinces in Canada. I don't know how many there are in India. The only one I know the name of is Kerala, K-E-R.
Kerala.
Kerala. Or say again?
Kerala.
Kerala. Thank you. The inflection's different. Kerala.
29 states.
29. Very good. So, and if you visit 30 of them, that means you visited one more than once.
Yes.
Right. Okay. What state are you from?
Gujarat.
Gujarat? Okay. Which is in West India.
Yes.
Okay, excellent. And so perhaps that would be the state I visit twice, right? If I visit If I visit India 30 times, I will visit a state more than once, right? If you visit the United States more than 50 times, we'll visit a state more than once. But everyone just visits New York every time. Okay. We're going to make no claims about which states we're visiting more than once, because we don't care. It doesn't actually affect us which state we visit more than once, right? The only thing that matters is we're going to be in a state more than once, and we're going to show why that matters in just a moment. Okay. So I got my string. I'm reading my string. I'm a deterministic finite automata. I'm thinking Q0. I'm thinking Q1. I'm thinking Q2. Oh, now I'm thinking Q1 again because I read a letter I'd seen before, right? That's sort of what's going on. Okay. We're going to define the sequence of states. Not too much matters in here. But we are going to have an I and a J, and we're going to put them in here at some point, and this is going to end at P, right? Or at more than P. It doesn't matter, right? Okay, so we're going to start with Q0, and then we're going to number the sequence of states. The thing to remember here is that when I have an S, that's referring to the state. Yes. And it is possible that a given state is named S sub I for more than one I. And in fact, it's necessary. Right? Okay. So, for all S sub I in the set of states, or in the sequence of states, S sub I is an element of Q, the set of states. S is an ordered collection of elements and therefore may have duplicates. It is a list. It is an array. It is a tuple. Q is a set. That's the difference. So there can be more of this than there are of that, even though they contain the same things. I don't know that we need to see an example. So, if I look at this, for all S, for all, I don't know, states in S, all state in Q for S for state in S. This is how I would write a for all in Python. I don't know if you can do length of set, right? So everything in here is in here, even though this is bigger than that. That's the trick. There is considerable amounts of information being stored in the arrangement of the symbols, not just in the symbols themselves. It's the same way 1, 0, 0 and 0, 0, 1 are different numbers, even though they have the same symbols, right? Okay. Cardinality P is greater than cardinality Q. Which, that's restatements. Therefore, there exists two values. And they are less than P. We're going to call one I and we're going to call one J. And the way we're going to pick those two values is we're going to find when we visit the repeated state. And we're going to say the first time we visit the repeated state is I, and the second time we visit the repeated state is J. That's all. So we take I and J such that Si is Sj. I'm pretty sure this P is supposed to be the cardinality of S. Okay. I hope when you go through the process of making a Corto book for this course, which remains what I would like you to do, I hope you get an appreciation for like writing this stuff down in a way that you've seen me a few times today, where I like read something I read. So clearly I was like tired or wrong or something when I wrote it. This proof still makes sense to me. If it doesn't make sense to you, that's okay, right? Your job is to write it down so that you understand it, once you do understand it, right? But like catching typos like that is like, when you can do that, that's when I will feel good about you understanding the material, right? When you're like, oh, you know, I was typing quickly, or like I wasn't thinking, or like, and like, this number is P. It's just lowercase p, not in brackets, right? So I was like very close to understanding it. And I meant it to refer to the cardinality of S. And you can believe me because I typed that into Python in front of you right before I revealed this, right? So this is like an oddly understandable error, but it is extremely wrong, right? P is not defined anywhere. This would crash your code if you wrote this in code, right? And it doesn't crash here because this is a blog, right? But catching those types of errors in your own work will be the rewarding part of this process, because once you catch errors like that in proofs, you're also going to find you're not going to write bugs in software, right? Yeah. Very good. Okay. Find x, y, z. Okay, how are we going to do this? All right, well, no problem. X is going to be everything until we get to S sub I. Note that those are A's. So I am now talking about letters or symbols. I am not talking about states anymore. I needed to refer to states so I could find what I and j were. And now that is a string. That is the string of the first I letters of x, y, z. We note that our machine is in state S sub j after reading x. Why is that? By definition. We set S sub I and S sub j to be the state that our machine was in after reading I and j letters, respectively. And then we picked I and j such that this machine was in the same state. And we did that by having a long enough string that we had to repeat a state. We're going to let y equals the string from a sub I to a sub j minus 1. This is the string in between the two repeated occurrences of one state. When we were taking the, we were doing the GNFA proof, and there was the sort of the edge, and then there was the loop, and then there was the other edge. I visualize this the same way. There's an x, and there's a z. And x and z go through some state. And there's a little loop at that state, and that state is y. Because when you read y, you go back to where you started. So we're going to start in some state s sub I, and we're going to end in state s sub I again. We have to do that somewhere because we have to repeat states at some point. Okay. So we note that after we read y, our machine is in the same state as it was before reading y. And then we're going to say z is the rest of the string. So the string is x, y, z, and y is the part of the string between the repeats. AP is the final letter. That's just the last letter, because the string is a length P. That is the jth character, which is when we were in the repeated state the second time. That's the ith character, when we were in the repeated state the first time. And this is the beginning of the string. When I drew out the removal, I did RST. It looks the same as the RST. XYZ instead of RST. And the reason we're now saying XYZ is we're not just changing the letters for fun. R, S, and T were supposed to refer to languages. These are referring to strings. So these are elements of languages. They're not the languages themselves. Okay. All right. M is going to accept after reading Z by definition because we selected an XYZ. It was an element of the language of M. Okay. We're going to pump on Y. The pump I always imagine is I had a manual bike tire pump growing up. And so I think of Y as my empty bike tire, and I pump it, and there gets to be more Ys every time. That's how I'm thinking of this, right? Let's take some notes. We note that the string xz, x concatenated to z, where we omit y, is accepted. This is the series of states terminating with the accepting state sp. We note it goes straight from I to j plus 1. This thing is of length shorter than p, because we take out a big chunk in the middle. There's plenty of ways to write this. I wrote this in interval notation, 0 to I, j plus 1 to p. Actually, the best way to write this is Python slices. I think I have slices here. XYZ is just Q naught through S sub p. And we can denote this the same way. We note that the initial and terminating intervals are the same, and we just have I plus 1 for j. And that is the repeated sequence. All right. A lot going on here. Well, what is going on here? It's not too bad. This is Q naught through S sub I, S sub I through S sub j, S sub I through S sub j again, because Si and j are the same, I through j, and then j through b. So we're repeating that sequence in the middle. We have a cycle. This is a cyclic graph. Our graph has a cycle in it, right? And we're just duplicating that section in the middle. In general, x, y to the n, z, is accepted by 0i, I plus 1 to j to the n, j plus I, or j plus 1 to b. I just take a sequence of states and I repeat it the same way I take a sequence of letters and repeat it. This might look easier in Python. I have some list of states. I cut at I and I extend to j. I should have an additional invariant here, perhaps for clarity, that I is strictly less than j, and it's less than j by quite a lot, by some relevant amount. We fixed y to be greater in length than 0, so it is necessarily smaller. Okay. So the states of x plus z are up to I and after j. The states of x plus y plus z are s, or s up to I to j, j to the n. X, y, y, z, up to I to j, j. Why is this so much easier with Python slices? This thing automatically stops at j minus 1, so I don't have all these minuses floating around that are really obnoxious. So Python slices are actually extremely good mathematical notation for this specific problem. And you actually see, to me, what happened when I was looking at this, I was like, Python is a better formal mathematical language for computer science proofs than some of the mathematical languages are, because this accursed indexing is taken care of for us. But how many starting programmers hate that this doesn't include j, right? Okay. S to I to j times 2.
Times 2 plus j2.
Right, this is the same thing. This is the same thing. These are equivalent. I could change these lines. Right? And I did write the infinite thing. I didn't run this. You'll notice that most of my Python, when I run it, code pops up here. I didn't run this because that's infinite. That is for every natural number. But if I could run it, if I had the hot new startup coming out of Silicon Valley that had computers with infinite computing power, right? I would just evaluate this statement and I would see, yes, for all x, y to the power n plus c, the states of that transaction are a to the I to the j, power of n, to the power of n times n, whatever, right? N, j to the n. That's all. Another thing I really liked being able to omit the 0 and the here. So I found the Python much more compelling on this example.
So we won't have a final result in this one.
We won't ever.
Final result.
We will. I would say we would always. Let's see. I see. It depends on what we mean by result. Okay, so for any string, we will always find the result. For every string, we will never find the result, because there are infinite strings of finite length. We can calculate over any of the finite strings, but we cannot calculate over all of them.
All of them.
And yeah, it's a very odd thing where there's an infinite number of finite things. Much easier with Pythonic slices. Graphically, let's do this graphically. We love our graphics in this class, I hope. Ooh, there'll probably be like course evals at the end of the term, and you can say like, I liked the Python, I liked the graphics, I liked the LaTeX. Let us know what worked for you, right? The hope is that You are the first of many, and we would like to do a good job. I'm worried that we're going to be making like everyone eat Indian food from now on, right? You'll have established the trend and be like, sorry, in this program, you're only allowed. If you don't like chana, we're sending you. Like, okay. So this is how I imagine it. Q naught, S sub I, Q of n. Does this look a little bit like the GNFI thing, or well, generalized, non-deterministic.
Finite.
Yes. Similar. I'm gonna pull that thing out, right? Okay. So what is on each of those? Well, I'm gonna label them X, Y, and Z. I don't know what's there. I'm just using variables. I don't know what's there, and I don't care what's there, right? The only thing that matters to me is I'm going to be able to repeat Y, whatever Y is, and I know Y is of length greater than 1, okay? This is a valid GNFA. Boom, done. Okay, all right. That's it. So after all of that proof, this is the only thing you have to do. Now all that remains, we went through all of this, and I know what you're thinking. You're thinking, what's an example of a language that can't be described by a GNFA? And we can prove one now. So now we just have to find one of the things that satisfies this. So Professor Sipser has a few examples. Before we do that, these are our conditions. I have seen the pumping lemma written down a lot of times. I have never seen it written down that well. Professor Sipser said something that I thought was very interesting. It's like, he doesn't think he would be able to figure out the inequalities. They are like aren't interesting to him. And I really get that, right? Like all these inequalities are not that interesting, but like we can go through them a little bit, right? The string is longer than the number of states. That one's not too bad. The string is in A. That's not too bad. The repeated string is not the empty string. That's not too bad. And we're going to take something where the prefix is less than the number of states, right? So we're going to have some leftover states in Z at the end, basically. That's basically just going to like help us in some proofs, and it is a reasonable assumption. So I think we can write this proof without needing that, but it's easier to need it. Here's some examples. Oh, I need to check the time. What time is it? Okay, it's 4:30. This was one of the first things we saw. Equal number of zeros and ones. Why can't we do this? Well, it's not so bad. We're going to assume it's regular, and then we're going to violate the pumping lemma, and then it will not be regular. Okay? Let's assume D is regular. That means we can apply the pumping lemma, direct contradiction. Okay. Let's take this string. By the pumping lemma, we need a prefix. And Y is the thing we're supposed to be able to repeat, right? So Y begins in position in state SI and ends in position SI, right? And also that happens under the pumping lemma. So what do? We take whatever the pumping length is. We have pumping length zeros and pumping length ones. And that should be recognized by our language because we said equal numbers of zeros and ones, right? So we're going to find the xy such that xy is less than the pumping. How are we going to do that? Well, we know that we don't have any ones in that xy. Why is that? Because we have p zeros, and xy is less than length p. So xy, every single character in both x and y is a zero.
Zero.
Has to be. And we've got to pump one of those things, right? And so we have to pump something that is of length more than zero, which means we've got a bit of a problem here. However long y is, we need to be able to take that many zeros out of this, and that still has to be a string. And whatever length y is, we need to be able to add that many zeros to this. But we're only adding zeros. We're not adding corresponding ones. And our language is equal numbers of zeros and ones. So we're in big trouble. We can't pump anything. Now, we would be fine if y was allowed to be of 0 length, but it's not. So we use our two assumptions here. Y's length greater than 0, xy less than of length p. And with those two, we derive a contradiction, because what we need, p minus cardinality of y, must be equal to p. Cardinality of y is necessarily not equal to 0. That is an inequality. That is a contradiction. This thing is not regular. It is irregular. And there we get our little box. That's what I do it for. I do it for the little boxes. Some people like to say QED. I do that too. Quod erat demonstratum. I think it's Latin. Let's do this graphically. Oh, we can't. It doesn't exist. That's the whole point. So one of the limitations of graphical thinking, when I was taking my atomic theory or whatever it was called, I think mine was called complexity theory, in undergrad, we would always say, why do we ever have to write the proofs? Why can't we just always join the automata? It's like, well, you can't do the impossibility proofs by picture because you have to prove that you can't draw the picture. So there's no graphic for this one. Yeah, right. So sorry. How could we draw a DFA that doesn't exist? All right. Okay, here's another one. This is strings that are repeated, right? We take a letter, or no, we take a word out of sigma repeated, because that's star, so that's any number of letters in any order. We repeat it. Okay. This is going to be quite simple, right? So we're going to show that f is not regular by contradiction. We just take 0 to 2p, no problem. You just take a string of certain length. This one is of odd length. Wait, what's the problem here? Oh, we can't actually pump on this. Why can't we pump on this? Well, if you add 2 zeros at a time, so like we don't know if 0 is if y is of odd length, right? We just know that it's of non-zero length. So we can't assume it's of odd length, and it's of even length. We still get strings of odd length, or of.
So you know that.
If the, okay, I'm going to start over again. Okay. We start a string is 0 to the 2p, or 0p, 0p. I would say, no problem. Take x and y any way you like. And we have to say that, right? Because we don't know how far, we don't know how long y is. The only thing we know is that y is of length greater than 0. What if y is of length 2? Well, if y is of length 2, then we have 0 to the p minus 2, 0 to the p. That's still part of our language because that's still repeated. It's just 0 to the p minus 1 repeated, which is allowed. So what we need, since we're only working with zeros, is we have to have odd length to show there's no repeats. But we can't achieve odd length if y itself is odd. And we can't prove that y is odd. So this proof doesn't work. We have to use a different technique. So this is just an example of a failed proof. This is where you can't say, oh, I thought about it really hard, and I'm pretty sure this is wrong. This proof will not go through. Your graduate TA at MIT would say, this doesn't count. I don't have a graduate TA at MIT. I'll have to grade them myself, right? Okay. How do we fix this? Very easy to fix. Put a 1 at the end. No problem. Because what's that do? Well, no matter how many zeros are here, how will be different than that number of zeros, which means this will not be repeated. Because we're going to have to pump in here somewhere, which means we're going to have to add zeros and take them away from 1. Let's take a look at it. So we're going to say our xy is less than p. What's that mean? All of x and y are going to be 0. That is There does not exist a 1 element of x, okay? So xz is going to equal to 0 to the power of p minus the cardinality of y. The cardinality of y is necessarily greater than 0. So this is no longer going to be repeated. Contradiction. Easy. This one was pretty tricky. I'm not going to give you a homework assignment on something this hard. This is just really cool. So I'm going to show it to you. We know that regular languages are closed under certain properties, like union and so on. Which means that if we prove something is irregular, we know everything that's a union with that is also irregular. So even if we can't figure out how to prove it for one thing, if we can show the union of something, so let's do that. Let's use a closure property. B is equal numbers of zeros and ones. This was from our very first slide. That one of these is irregular. Which one? Now we can prove it. It was the first of the two things. We're going to assume by contradiction that B is regular. How am I going to do this? Well, isn't this interesting? 0 star 1 star is regular. And I would like to point out I am cheating with notation here. 0 and 1 should both be in sets because star applies to languages, not to characters. So that should be the set 0 and the set 1. Because this is a language operator, not a string operator. Does that make sense? This means repeat the number of elements in that set, not return the number of times. Yeah, so I have a type error here. I'm allowing it, but I am pointing it out to you because I don't want you to be confused. And I went back and forth on whether to write it that way. But. Okay. So this thing's definitely regular, right? We know it's regular. It's literally expressed as a regular expression, right? And we are assuming that this thing equals numbers of zeros and ones is regular. B is the language with equal numbers of zeros and ones.
Zeros and ones.
Yes. And you'll notice I did not write that as a regular expression, and there's a reason for that. It's because it's impossible.
So how it is then regular?
It's not. Well, you see, this thing has to be regular under contradiction if this thing is regular. If B is regular, B intersect 0 star 1 star is regular. And that was the first thing we proved wasn't regular. So that means this thing isn't regular. So this is a way you can say, like, oh, I don't know the ordering, but hey, maybe I can impose an ordering with intersection with a regular expression. And then I can prove the ordered one isn't regular. This is how you actually use the Pumpy-Lemon practice, because these strings are going to be so chaotic and nonsensical, right? And you just say, I sort the string alphabetically, and then I prove the alphabetically sorted string is not regular. I say, oh, fair enough. There's nothing you can really do about that. So this is very cool. Think about this for a long time. I had to sleep on this one. Stretch break. It's 4:30. Okay, I'm going to keep going. Or do you need a minute? I'm going to introduce context-free grammars.
I just feel I just want to.
Yeah.
Give me a minute.
Cool. All right, okay. Congratulations. You graduated the DFA portion of this class. Think about it. What did I say at the beginning of class? 12 and a half hours on automata theory. For 6 are over right now. You get another 6 on this. Half hours lost in noise, right? So we're going to do basically 6 hours of context-free grammars. The cool thing about automata theory and computability theory, which is automata theory or the Turing machines, is like they sort of blend into each other. The precise introduction of the Turing machine counts towards both things because it is both the automata and it is the computer, right? This is the most powerful non-computer automata, the context-free grammar. Absolutely 100% the linguists cooked this up. This was not the mathematicians. The mathematicians went in and found an automata that was equivalent. The way I think of it is the mathematicians had the finite automata, the linguists had context-free grammars. They met in the middle, the linguists generated regular languages, and the mathematicians generated push-down automata, which we'll see tomorrow. Context-free grammars are very cool. I think they're used a lot in programming language theory. Of the things in this course, I remember hearing of finite state machines and automata, and the context-free grammars first. I think it's not obvious what context-free means. I'm going to say you'll see. There's a cool reveal with like a understanding check later, where I'll say, no, that one has a context, and then you'll know what a context means, right? So for now, just say it's just word salad. It's just context-free grammar. It's just a thing that is, right? Last one of the day. Okay. Context-free grammars are described by rules. A rule is very, very close to a lambda expression, right? They're not as powerful as lambda expressions. They're pretty powerful. Context-free grammars have a formal definition. They are not an automata, so this is much closer to defining regular languages again. We're going to look at some examples, and then we're going to look at this thing called ambiguity. It can be ambiguous how a context-free grammar generates a language. Okay, rules. This is what a context-free grammar looks like. It is almost always stylized this way. In the upper left, there is the name of the grammar, which is usually G with some subscript. This is G1, because this is our first context-free grammar, and we are 1 indexing in this course. Beneath the name of the language, there is a series of symbols. They are all symbols. And on the left-hand side, there are singleton symbols, and on the right-hand side, there can be combinations of symbols. And we use an arrow here. You don't have to use an arrow. What this really is, a context-free grammar is a set of tuples. That's all. And the tuple is singleton string tupled with multiple string. So singleton string, multiple string. This is an ordered pair. This is a set of ordered pairs. That's all. Depending on how you count it, sometimes order matters. So people might say the whole thing is a tuple instead of a set. Not super important. This is what it looks like. That doesn't make sense yet. But there is one thing that should jump out at you, which is that there. That's little sigma. That's the empty string.
Empty string.
So this substitution rules. At any time when you have an R, you can substitute it for nothing. All right. I was all over the place on how to denote the empty string at various points in this class, but I'm going to use a little sigma beginning with context-free grammars. Okay. So what's a rule? Okay. We're going to turn these rules. What are they of the form? They have a symbol, they have an arrow, and then they have a string of symbols. You could argue that the initial symbol is actually a string of symbols of length 1. It makes no difference to me, right? We're going to take one thing to many things. Multiple things, potentially just one thing, right? Rule is a statement of this form. Variables they're not mathematical variables. They're something else. They're a special type of symbol, and they're the subset of symbols that appear on the left-hand side of the arrows. In my example, there were only 2 things on the left-hand side, capital R and capital S. On the right-hand side, there was additionally a 0, a 1, and a little epsilon. So, okay, Not every symbol is a variable. Every variable is a symbol. The variables are a subset of the symbols. The other kind of symbol is the terminal. Terminal is a complete symbol. It is done. It is finished. These are the symbols which appear only on the right-hand side. Now, the reason these are called terminals is because the rules are called substitution rules. And you can substitute something on the right-hand side for a terminal. So if you are working with a string and it contains R, you can substitute something for R. But if it contains 0, you cannot substitute anything for 0. 0 is a terminal, R was a variable. Now, there's nothing intrinsically about 0 and R that cause them to be variables and terminals. The only thing about it is, it's on the left-hand side, it's a variable. If it's only on the right-hand side, it's a terminal. But variables are also allowed to be on the right-hand side. The starting variable is by convention the topmost symbol. There's ways around that if we need to. And so when we're going to use a context-free grammar to do the thing we do with all of these grammars and languages, we're going to generate a language with it. So in order to see if a string is in a language, we will start with the starting variable and perform a series of substitutions. And if we can get to that string, it's part of the language. Here's an example of 3 rules. S becomes 0, S, 1. S becomes R, and R becomes, yes, the empty string. So we have 2 variables and 2 terminals. The variables are S and R. They appear on the left-hand side. And the terminals are 0 and 1. They appear on the right-hand side. Let's go through a process of generation. We're going to write down the start variable, and then we're going to use any substitution rule. In our example, there were 2 substitution rules. There was S becomes 0, S1, and S becomes R. We're going to substitute any variable for any variable until no variables remain. Only terminals. That's why they're called terminals. When you have only terminals, you terminate. That's your return value. You can think of this as a loop that says while terminals in string, or while intersection of terminals and set string, right? We're going to loop until there's no terminals left. Okay. Only terminals. Only terminals. Every possible string that can be generated by the grammar is the language of the grammar. This is getting a little weird. I think it's a strong claim to say that a grammar has a language. I think a grammar is a language. I'm going to use L to denote when I am talking specifically about the language, which is the set of strings, rather than the set of substitution rules, right? Let's go through our example. We're going to start with S, because it's the starting symbol. We're going to perform a substitution. We're going to substitute S for 0, S1. We're going to do an additional substitution. We can substitute 2 things for S. Let's do another 0, S1 substitution on S. Does that make sense to you?
How do we make 0, 0, S1?
So we can say val as S. We can say val dot replace. We can update val. So we can do this indefinitely, right? These are substitution rules. This is how they work. Same as strings. And remember, these are the linguists, so they were only playing with strings. They weren't thinking of binary at all. They don't care about binary, right? What's another example of a substitution rule? We can substitute S for R. And what's an example of another substitution rule? We can substitute R for nothing. That's only terminals, and we're done. Substitute S for R, substitute R for nothing. Done. Here's another example. S, 0, S1, 0, R1, 0, 1. This is creating the thing that we just proved was irregular. This is B from the earlier slides. The last thing that we showed the pumping mama on. That's how easy it is to express with a context-free grammar. In fact, it's easier than this. That is an example that is large enough to contain interesting things. Right? This is a derivation tree. Look at what's happening. We progress temporally. We start with S. We perform a substitution. These are terminals, so they will be unaltered, so we leave them as is. We could persist them all the way down to the bottom of the tree. That's a graphical design decision. We take another S, we perform another substitution. We keep the S, we substitute the R, we substitute theta. The way we read this string is we go around on the outermost edge, 0, 0, 1, 1. Here's another way to visualize it. The first S is split into 0, 1, and an intermediate S. And the second S is split into 0, 1, and an intermediate S. The third S is turned into an R, which is turned into a nothing. 0, 0, 1, 1. This is, we can express it this way. That's not regular, right? That is a closed form solution. This is a language a CFT can do that a DFA, NFA, or GNFA cannot express or generate or recognize. We can use some shorthand. This is I think, in my view, a helpful shorthand. Instead of writing S twice, we can use an OR R. S becomes either 0SI, 0S1, or R. Let's do the formal definition. Okay, a context-free grammar is a four-tuple. I'm going to tell you right now, I'm pretty sure that V is going to stand for variables, and I'm pretty sure that sigma is going to stand for the output symbols, because that's what we've used them before. V is a finite set of variables. That's why we call it V. Oh, come on, you knew that one. Okay, what's sigma going to be?
Set of
The alphabet.
alphabet.
Yeah. It's a finite set of terminal symbols. The same sigma we used for the DFAs for the regular languages, right? Wonder what R is going to be. Oh no. Okay. R is the rules. What is a rule? A rule is a tuple. It's an ordered pair, right? It's an ordered pair of a variable and a string that contains elements of the variables and the terminal symbols. Variable, arrow, variable, union, terminal, which is R. Yep. And S is the start variable. We just have to specify our initial state. Right. So S is a subset of B. Or it's an element of B. It's not a subset. Let's do some substitutions. For all U, V that are in variable.
Union to sigma.
The variables and the terminals.
Terminals.
Yep. Or the output symbols. I think it's probably more natural to refer to it as sigma than terminals, right? If V is derived from U, there exists some rule such that R of U is equal to V. Okay. If U, and so we're just introducing, so this is an arbitrary number substitution. Don't worry about this too much, but this means that there's a sequence of substitutions. Transitive closure. Do you know what a transitive closure is? If I'm friends with Barack Obama, and Barack Obama is friends with Michelle Obama, then by the transitive closure of friendship, I am friends with Michelle Obama. So it means has friends with is transitive. If I am a friend with you, then I'm a friend with your friends would be the example, right? These exist in real life. I flew here on Delta Airlines. The transitive closure of Delta is just about every airport in the United States. Because even if you can't fly straight through from anywhere to anywhere else, right, everywhere is connected by Delta. The transitive closure of Delta flights. Whereas straight through flights are this one. So that's drive, that's connect. I can't believe I couldn't think of someone to be friends with other than Michelle Obama. That's very embarrassing for me. I should have said Jimmy Carter. Okay. We term this the derivation. And if it is a derivation from something, unless it is from the starting variable, then we just omit what it's from. So I can say, yeah, I don't know how often I say this, but we can say 0011 has the derivation s to 0s1, s to 0s1, s to r, r to sigma. That is an example of derivation. This is mostly just a way to write words down, right? The language of a grammar is the words such that the words are an element of sigma star, so only terminals. Words can only contain terminals. And there exists a derivation from the starting variable to that word. Only terminals can be derived. That's all. All right. Which of the following is a CFG?
C1.
You like C1? Okay.
Because it has, B2 below B1.
So this is how I'm going to get you.
R.
Those ones.
C2, R.
Yeah.
You have to like little sigma, nothing. So this must.
That's what I thought too. I was also wrong. So C1 is actually a context, or it's not a context-free grammar.
Oh, it's not a context?
And the reason for that is because there's context. The context is the 1 and 0 on the left-hand side. We can only have singleton variables on the left-hand side to be context-free. That's what it means to be context-free. You perform the substitution without knowing what's there. C2 is a well-formed context-free grammar that accepts the empty string because it never terminates. So you correctly pointed out, like, that's never going to produce any string. It's not. But on the left-hand side, it has variables, and on the right-hand side, it has variables and terminals. So it is, by definition, a context-free grammar. Because it produces no strings, the language it produces is the empty language. Because it can never produce anything without variables in it. So that's ludicrously annoying. But this is what context means. Context means singleton's left-hand side. That is more important than the fact that it actually produces a language. Here's another thing.
Singleton left-hand side or right-hand side?
Left-hand side, on from the arrow. So
From the arrow. Okay.
there can't be both a B and a 1 here. There can't be both a 0 and a B here. That's not allowed. Because this is considered the context, the relationship of two letters to each other. That's what the, I don't know, logicians, grammarians, whatever, the linguists. This has a context. This happens to be the empty language. Anyways, I thought that was an unfairly hard question, but it was in the course that I took, so I gave it to you. You know, we pass on. Okay. Also get an example. This is a fun example. Do I have 30 minutes of voice left? Oh, gosh, okay. We'll end a little bit early because I won't be able to talk. Okay. E denotes expression. T and F doesn't really stand for much of anything at all. Times, I think. We can take an expression and say that it is an expression plus some other expression, a summation, or it is a t. We can take a times expression and say that that is a times expression cross a finishing or final expression. So this is the final expression of the times value. I think that's what that means, right? Or it is just the final value. And then we can say the final value is equal to an expression enclosed in parentheses, or it is equal to some character a. This just means literal a here, but you could also take this to mean any numeral, right? You could say this is a variable. Doesn't matter. The variables are ETF, which I think of as expression, times expression, and final expression. Our terminals are plus, times, paren, and a. Our rules are as shown, and our starting value is 0. This is how we build arithmetic expressions. And at this point in time, you should say, wait a minute. How much of mathematics can be done with a context-free grammar? And quite a lot of it. Right? All elementary mathematics, right? You have to start doing things like summations before you can do a context-free grammar. Okay, here is a derivation. How does this work? I take e, I substitute e plus t for e. E plus t?
E plus t.
Yeah. I substitute, what is this substitution?
T plus t.
Yeah, which one is this? Yeah, t becomes t times f, t cross f, and e becomes t at the same time. Ah, yeah, this is a double substitution. E goes to t.
E t to e plus t plus t into f. Oh, no, never mind.
Look at the tree. The tree's easier. E goes to e plus t. That e becomes a t. That t becomes an f. That f becomes an a. That plus is terminal. E goes to t. T goes to t cross f. T goes to f. F goes to a. Times is terminal. F goes to a. A plus a times a. Easy. It's like falling off a log. This is impossible. I did that question. A plus a times a. It would not be the best programming language in the world, but you can write a programming language with just context-free grammars. Let me show you a grammar in my doctoral thesis. I worry people don't believe me when I say this stuff. There it is. You can't have E or theta left in an assembly program. Those aren't assembly commands. So we have to keep substituting them until we get an actual program. But you can have an instruction applied to an expression, or an or over expression. So this is the grammar of properties I generated. You can decide if you think that's cool or not later. You'll probably think it's cool in like a few years when the pain of this weekend has worn off, right? Parse trees may be used to encode precedence. So the linguists, who are not as strong in computer science as they used to be, and I think that's mostly a bad thing, but I also think programming has become relatively mature, and there are languages like Python and Rust that are pretty good. Though probably we would still benefit from forcing every undergrad to take like 2 years of linguistics or something, right? This is how you do operator precedence. You say, all right, here's a Python expression, start matching it. And you compile it down into different things, and you do all of your times and your exponents before your plus and your minus, right? I find it very, very annoying that it's possible to evaluate that in Python, but the linguists say it's okay. let's see. I really don't like that. And I especially don't like that because that's false. These are called chained operators, and I hate them, and I think no linguist would have allowed Python to have them. But essentially what this is doing which ones? Yes. One. It's logically equivalent to this. Which, to me, that makes no sense. So that's what you get when you don't have enough linguists on your team. That's not context-free. Because the context of what this evaluates to is dependent on that. There exist grammars that can be derived in different ways, and in this case, they do not have operator precedence. I think it would probably be a good thing if that were equal to 9. I think that probably should equal 9. No one wants that to equal 9 because all of the code in the world would break, right? But if I show that to a young person who hasn't been trained in order of operations yet, they immediately recognize it as 9. And I don't think they're wrong, I think we are. Right? It just makes a little bit too much sense to think of it as this, right? Just a little bit too much sense, right? And so I think this ambiguity that exists is, it's not the worst thing in the world. I understand that spoken language, so we've been speaking much today, trying to explain things to each other, right? Spoken language is extremely ambiguous. It is very good if you basically already know what you're trying to communicate with each other. And if you're trying to teach someone what a context-free grammar is, that's not necessarily going to work, right? So I rely on the slides quite heavily. Other people do other things, right? Let's introduce a notion of ambiguity. These two grammars both produce the same language, but G2 produces it unambiguously, and G3 produces it ambiguously. And I'm going to demonstrate this by finding A, I think it was A times A plus A. And I'm going to find it in 2 ways with G3. Let me show you. So here's G3. I can substitute the plus first. That's supposed to be a times for sure, right? And then I can substitute the plus first. So I can do times first or plus first. That's a significant typo. And then once I do the plus or the times, then I do the other two. So after I have A plus something, I can turn that into A times A. Or after I have E times A, I can substitute that for A plus A. And this is a legal interpretation of E becomes E plus E, E times E, E paren, or A. Does that make sense? As soon as I do that, I can go in different directions. The closing thing is this Python exercise, and I'm a little too fried to want to go over this right now. So I'm going to tell you to look at this for at least 20 minutes tonight and see how you feel about it. But what I will say here is these are the string replaces from that grammar. And this is not quite right. And it's not quite right for a sneaky reason. So there exist things that can be produced by the grammar that cannot be produced by this script. And take a look at this. I don't know how strong you are with like writing lambdas and list comprehensions and stuff, right? This is a dispatch table, which gives a bunch of people right. That's a tuple of functions. So depending on how you are with your scripting, this might be painful to work with. But at least look at it and see if you can come to a sense of how this works. And you might be better off if you get stuck on this, trying to implement the unambiguous one. Might be a little bit easier. Okay. Does that make sense?
Yes.
Cool. I can't talk anymore, so we're done. Do you have any closing questions?
Not right now, actually.
Yeah, just think about it.
Yeah.
Yeah. All right, I'm going to pull the string down.